Hi, and welcome to the 2023 Research Review for the Software Engineering Institute here at Carnegie Mellon University. My name is Tom Longstaff. I'm the Chief Technology Officer here at the SEI, and I am just really pleased that you're here either live with us or watching the recorded version of what I think is going to be an interesting set of panels for the lead investigators of some of our most important research. Our whole theme this year is cultivating curiosity. And what do I mean by cultivating curiosity? Really, it means that not only are we asking questions and evaluating particular practices, but we're taking advantage of the most recent technological advancements in AI and cybersecurity and software engineering, and really wondering and asking questions, how can we take those advances and really leap forward with regard to the kinds of innovative solutions we can create for the Department of Defense, for the world, for all of us to do a better job of incorporating that technology into our everyday lives. What you're really going to see over the next couple of hours are the people who really do the work here, the actual investigators asking these questions, being curious, coming into all of this to really understand how this technology is going to shape the future for you, for the Department of Defense, and for everybody. I'm going to use as an example something I know all of you have been hearing about for quite some time now: generative AI, large language models, ChatGPT, any of these kinds of things that are out there and available for you to try. What has happened, especially over the past year, is the amount of curious investigation into what can these technologies do for us. Go to ChatGPT, generate a story, now generate it as a limerick, now generate it as if it was being taught by a school teacher, now generate it as if I want to make a professional letter. All of these things are just the curiosity of how to apply some of these new technologies into your daily life. Some of them may work out and may work out great. Some of them you'll play with for a day or two and say never again. Some of these things will actually create a spark of creativity and innovation that leaps over the existing technology that we have today into something that we've never thought about before. At the core of all of these new technologies like generative AI is a synergy of the technology disciplines, a hybrid of bringing together, and for us that's software and cybersecurity and AI into these kinds of hybrid solutions that actually generate the innovation. We had a great SEI blog done by our CEO and director, Paul Nielsen. It's well worth the read. It's going to be up on the website. We'll have links to it so you can jump right to it. But it really talks about specifically the synergy among the engineering disciplines of software, cybersecurity, and AI to really begin to say, how can that create solutions that we've never thought about before in sort of Making cybersecurity more accessible, making it easier, making it approachable. How do we get software engineering to incorporate faster, better, cheaper ways of getting better quality attributes across all of our systems? How can we get it to understand architecture in a way that allows us to go away from manual investigation to far more automated investigation in terms of specifically talking about our software? And finally, AI for mission, AI for improving our lives has to incorporate these ideas and these elements in so that what we use is fair and responsible, as well as having those engineering trade-offs that allow us to build repeatable systems over time. That's the real key to engineering. How do I actually create a standard for engineering of all of these new technologies and innovations that we have that allow me to explicitly define the trade-offs, explicitly define the processes and characteristics and analyses that let me predictably create the solutions that we can rely on and trust moving into the future. So, for this year, we have 4 panels that we'd really like to have you watch and talk to. Imagine it like this. There are videos online that have deep presentations from every one of our principal investigators from each one of our projects that we're going to talk about, as well as promo videos. Consider what we're going to be doing over the next couple of hours to really be the idea that you've seen the talk, and now you're going to go sit in basically a breakout room or an outside hallway to the conference room and get a chance to really talk to, understand, and ask your questions of the people that are doing the research. For those of you that are online with us live right now, I hope you'll take this opportunity to be curious yourself and to ask questions that we will take live here, and basically I will help to moderate with our panelists to really get their insights, not just on the work that they are doing, but how it might affect the solutions that you need. The real benefits that you see might come out of this work that we have in the future. That's very important to all of us here at the Software Engineering Institute. We do basically applied research that allows us to take fundamental research areas, apply them to very specific instances that are there, and transition them for the benefit of the Department of Defense, the U.S. government, and the world that comes out that way. So, we've got national defense priorities that we've sort of grouped our panels around, starting with the idea of trusted AI and autonomy. What do you have to do to trust AI? What do you have to do to actually be able to run a system and say, I'm going to trust the output of the system in a critical decision that I have to make, or a function that I have to do, or something I'm relying on my technology, like my automobile or my airplane, to do for me? What does it mean to trust it? How can I trust a system that's helping me scan resumes for people that I want to hire? How can I assure that the implicit biases of those systems are not really taking and making the situation worse that I was sort of in there? How can I look at some of these various areas, especially with regard to the way systems are moving, and understand when they will and will not work for me? Advanced computing and software, we've got sections that are really talking about how do we go into the software side and trust the solutions that we have. Trust them to be deployed, actually be certified, and understand. For decades now, we've been thinking about ways to do formal analyses, formal methods, investigations of our software to make sure that we can really trust those things in critical areas. Frankly, it's been hard. As software gets more and more complicated, as system integration gets more and more complicated, the idea of doing complete formal analysis across everything is becoming farther out of reach, not closer. We have approaches based on our curiosity on what would it take if we could actually begin to investigate maybe doing some portions rigorously and some portions less formally. How would you bring those together in a rigorous way that allows us to do the engineering trade-offs? Then we get into the whole idea of how do we make sure that we've got the security that we need on these systems? How do we actually make sure that we have the kind of trust so that these systems can identify malware, they can be repaired, they can actually be fixed in real time, so we don't continuously expose ourselves, both within critical areas of the Department of Defense, but also in general areas of just software deployment, so that we're not all more and more vulnerable as we take on more of these capabilities and bring them in. Finally, an area that I think is important to all of us is, what does the future of computing look like? How do we investigate quantum computers? How do we incorporate quantum computers into our architectures in a way that we can actually improve our ability to go beyond scaling just with more and faster chips? How do we actually break out of the pattern of trying to get exponentially harder problems done with linear increases in the work that we have? How can we break out of that system and really get there? And how can we create more and more reasonable computing platforms that have the kind of accelerators built into them and the kind of specific systems on a chip that we can actually get them deployed directly, rapidly, and effectively into areas on the edge, areas that are moving, areas that we rely on to do everything around here that we're doing. So our approach this afternoon, these 4 panels we have some really brilliant researchers who are going to talk a little bit about the implications of their research, about their ability to really take the research results and make a difference. I really encourage you, if you haven't watched it yet, each one of these has a longer, more detailed presentation online. When you get an opportunity, if you haven't already done so, please go back and watch those videos. Get a sense of exactly what the research areas are behind. And if you watch the rest of these panels as they come up, if they stimulate areas that you have a question, or you get curious, or you really want to come into effect this way, I encourage you not only to contact us now during this session, but use the contact information we have to reach out to us as we sort of move forward. We're going to be diving into our research. We're going to be getting into exactly what the panels are going to be in. We're going to bring them into place. And we're going to get as detailed as you want to get with your questions in terms of where this research is, where it can possibly go. On the left-hand side of the chart you're looking at is a very simplified version of how it is that we work here at the SEI. And what we're doing right now is part 1 of this. It's the communication side. We want to engage with you. We want to understand the specific elements of your questions and your problems and your desired solutions that you really want to get out of this engagement between software, cyber, and AI. If you have elements that you need to have solved, we want to know, because that gets into this second portion that we have on the left, the research development. We take all of this information and it's what we use to define our future work. You'll see in a lot of the panels that we have coming up, the ideas that are being generated today all came from curiously looking at how does the new technology change the nature of what we're doing. How does being curious about the way AI can be incorporated, new cybersecurity areas can be incorporated, new open source frameworks can be incorporated to create solutions in areas that nobody's ever thought of before we actually came up with these kinds of answers. And then finally, we're always looking to integrate the kinds of solutions we have now directly into your workflow, into areas that will directly improve the nature of the work that you do every day. That integration can be easy. Sometimes it's just incorporating a technology, but frequently it has to do with lowering the friction between the work that you do right now and the integration of the groundbreaking technologies that will truly make a difference within your organization. So as we think about those sorts of incorporating the research and getting that research into your systems, think about how what you hear on these panels, what you see in these presentations, can effectively change the nature of your work, and what can we do to help that work change so that we can incorporate those new ideas that are coming in. So today, listen to what we're doing, what we're working on. Take notes, ask questions, be curious, but tomorrow, write to us at info@sei.cmu.edu. Visit our website. Come to our podcast. Look at more information. I hope this begins to spark your curiosity to know more about what the innovative research is that happens here at the Software Engineering Institute. So for now, I encourage you to take a look at the promo videos, take a look at the things that are out there and moving right along, understand where the questions are going to be, and really, at the end of the day, decide how it is that you want to engage. Where does your curiosity lead you? Where does it lead you to really think about the areas of work that you want to do? Because ultimately, at the end of the day, we don't do research for our sake. We do it for yours. And we'd really like you to be able to understand our work and incorporate it to solve the hardest problems that you have. Thank you so much for listening to this. We're going to take a short break. Please enjoy the promotional videos of the next two panelists that we have coming on board. And I'll be back in just a few minutes to incorporate and begin our first panel. Thanks all very much. See you in a bit.
Hi, my name is Anusha Sinha, and I'm a machine learning research scientist at the SEI and the principal investigator for the project focused on leveraging adversarial machine learning techniques to perform fairness evaluations. As one of the largest employers in the world, the Department of Defense is interested in applying machine learning to workforce management tasks to improve efficiency and accuracy. When using machine learning to make decisions that directly impact humans, it is important to consider underlying bias in these systems that can result in unfair decisions. We noticed that machine learning models that are used to screen resumes are often fine-tuned from large public foundational models. It is therefore important to understand and quantify how bias from these foundational models impacts child models that are fine-tuned from them, especially ones that the DoD might use. In this presentation, I will discuss two types of biases that can transfer from foundational models to fine-tuned child models. First, I will discuss how stereotypical examples of classes transfer from foundational models. Then I will explain how we use the results from this initial work to design experiments that directly measure how performance disparity between majority and minority groups can transfer from foundational to child models. Finally, I will talk about how our work can inform best practices for fine-tuning machine learning models to mitigate bias. Please join me at the SEI's Research Review to hear more. Thanks.
Hi, my name is Violet Torrey, and I am the principal investigator for the Moving Explainable Artificial Intelligence from Research into Practice project. While advances in deep learning have led to exciting computer vision and natural language capabilities, they also amplify existing challenges in working with opaque models. A lack of transparency about AI decision-making processes can make it challenging for end users to determine if AI system suggestions are right or wrong, or to build justified trust in system outputs. Research into Explainable AI, or XAI, aims to address a lack of system transparency by providing humans with explanations they can use to reason about AI predictions and behaviors. Our presentation highlights the SEI's work moving XAI techniques from research into practice. Through our 2-year explainability project, our team of SEI and HCII researchers is investigating practical methods for implementing XAI through a case study implementing explainability for computer vision algorithms. Our work proposes a 6-stage process framework that AI practitioner teams can employ to meet end-user needs, prototype and evaluate potential explanations, and maintain explainability software in the long term. To learn more about how our research addresses challenges in navigating explainability for real-world systems, join us at the 2023 SEI Research Review.
Welcome back. I'm glad you stayed. We're going to have a great first panel coming up right now. And I am going to jump straight in right off the front and ask our panelists to please introduce themselves, talk a little bit about how long they've been at the SEI and what their areas of research focus are. So Anusha, can we please start with you?
Sure. So hi, my name is Anusha Sinha. I'm a machine learning researcher here at the SEI in the AI division, and I've been with the SEI for 5 years now. My research interests have mostly focused on adversarial machine learning, and now I'm sort of transitioning more into looking at the fairness of machine learning models.
Great, thank you. Violet.
Yeah, hi everyone. I'm Violet Torrey. I'm a software developer and researcher here in the AI division, and I've been here for about 3 years. And a lot of my work looks at trying to build more human-centered AI systems and then also developing rigorous T&E practices.
Thanks you both very much, and thank you for being here. It's wonderful to have both of you together, and talking about these various areas. Before we start, just to give everybody an indication of sort of the nature of the research questions that you have in your current projects. Violet, we'll start with you. Can you talk about what the key research area and questions are in your current project?
Yeah, so there's a lot of work that looks at explainability and other transparency mechanisms, but there are some challenges in actually applying those in practice. There is a lack of guidance about how to pick up a system and actually make it more transparent for end users, for developers, for different kinds of stakeholders. So our work is really trying to figure out what does explainability in practice look like and how do you effectively make your system more transparent.
So what do you mean by more transparent in that particular case?
Yeah, so a lot of models, especially contemporary models that are really powerful, are using deep learning, and so these models are really hard to interpret, and it's challenging to figure out how they're making decisions. You can run testing and evaluation looking at how it performs on different testing data sets, but it can be difficult to figure out why did that model actually make that decision given an input. So explainability techniques, they're one method for improving transparency. They help you see kind of what the key factors were on an input to figure out what was important in the model making its decision. So this makes the overall decision-making process more transparent, giving people involved in oversight roles or also using the system a better idea of how it's working.
That's really great. But these are just computer programs, right? Can't you just look at the weights and say that's why the answer came out?
Yeah, that would be awesome. And there are some models that are more interpretable where you can do that basically, but when you're working with thousands, millions of weights, it can be really difficult to figure out what's going on, and even the people who are directly involved with building the architecture and training the models can't really tell you what's going on. So you need transparency methods to really make that possible.
Even billions and beyond these days,
yeah,
right?
Yeah,
I mean,
absolutely.
Just tremendous numbers of variables and weights and elements that are there.
Yeah.
Thank you. That's excellent, excellent. Anusha, can you talk a little bit about the key research areas within your project?
Sure, yeah. So my project is largely focused on properties of foundation models that kind of persist through fine-tuning. So as you kind of mentioned in your intro, people are using these large public models like, for example, ChatGPT and these other foundation models. And it's increasingly difficult to sort of train those models from scratch. And so people are sort of taking them from public sources and then fine-tuning them for more specific kind of use cases with smaller amounts of data. And so my work is sort of focused on understanding, are there properties of these foundation models, such as fairness, which we can quantify through a number of different metrics, that sort of persist through fine-tuning, or are there biases in these public models that we should worry about being carried over to the fine-tuned models that people are using, often in very high-stakes situations?
Excellent, excellent. Can you help us understand a little bit what it means to be fair, for a model to be fair?
Sure. So there's a ton of different definitions, and I guess it's very different depending on sort of the specific context that you're in. But you could, for example, want your model to have maybe equal accuracy on various subpopulations over that you're running the model over. But there's also, you could want to ensure that maybe you have equal selection rates for different subgroups. And so there's a number of different definitions that you can use, and there isn't really always one answer for the best metric that you should be using when you want to talk about the fairness of a model.
From your video that you have, the more detailed video in your project, can you give us one example of what fairness really looks like in practice when, what if I were using a model?
Yeah.
What would it look like for that model to be unfair?
Sure. So, for example, one metric, the metric that we're using in our experiments actually is this like disparate performance metric. So basically, we want to determine how different is the accuracy on different subgroups in the population for these different models. So, for example, you could want to ensure that the accuracy over a minority group is pretty comparable to the accuracy of the model in general, or the accuracy on the majority group, even if you have like maybe less representation of that minority group in your training data for the model.
So what's a minority group when it comes to this data?
So it can vary, again, depending on your data set, but often it's maybe people from like certain races that are historically have been like sort of underrepresented in data sets. But it could also be like gender minorities, it could be age minorities. It really varies depending on like the specific application of your model.
Okay. So basically, why did you choose performance as one of the key areas of interest within it? It sounds like, it's pretty clear. You just sort of make sure the minority stuff is treated fairly, and then you're good. So what role does performance play?
So I guess the reason that we wanted to focus on it was specifically because I'd done a literature search and I'd had some conversations with stakeholders, and it seemed like it was really important to them. And just generally in the field, it's one of the most popular like fairness metrics that people use, because it's sort of like the first question that you might want to ask about your models. Like, is it because often people when they're evaluating these models are looking at just like accuracy across the whole population. So sort of the first question that maybe comes to mind is, well, is that metric that we're already kind of looking at in general kind of equivalent across these different subgroups?
So you said the magic word accuracy.
Yeah.
Right? And that's what everybody thinks of when they say, oh, if my model is accurate, it's got to be good enough.
Yeah.
So what's the difference between accuracy and fairness?
So there's some definitions of fairness that are like sort of based on accuracy. So the one that I mentioned is like you want to ensure accuracy is equivalent over these different subgroups. But there's other definitions of fairness that are very different. So for example, one of the other definitions that we're interested in looking at is it's called equality of opportunity. And the idea is that you want to ensure that your model is sort of selecting individuals from these subgroups at like a sort of similar rate. So basically, like, let's say you have a model that is trying to screen resumes. You want to make sure that it's giving sort of like an affirmative response to people from a minority group versus the rest of the population at approximately the same rate, and it's not like more likely to give people from the majority group like a favorable output.
Okay. So you said there's a lot of different ways to measure fairness,
Yeah.
and a lot of different ways that are coming. Are there any other kinds of new fairness metrics that are coming out, or any ways that you're planning on expanding the notion of fairness in future environments?
So I am interested in looking at sort of how the like bias and selection rates can also transfer from foundational to fine-tuned models, and that's sort of like the next step for my project is kind of running some experiments specifically on that metric.
Oh, that's excellent. Sounds like there's some trade-offs involved in that as well.
Yeah. So that's kind of whenever you're trying to optimize for fairness with these machine learning models, you usually have to pay some sort of performance penalty in order to get improved fairness. So like the canonical example of that is let's say you train a model that has like 70% accuracy on your majority group and only like 20% accuracy on this minority group.
Wow.
And so one way you could make the model more fair is just by reducing the accuracy of the entire model to 20% on everyone. Yeah.
That sounds not so good.
Yeah. So obviously like there's I mean that's like a very extreme case, but there are a lot of sort of bias mitigation strategies that can kind of cause that to happen. And so there's this trade-off that emerges between, you want to have generally good performance, but you also want to generally treat people fairly or equally, and they're often in conflict when you're trying to I guess like optimize.
So I definitely want to come back to some of this idea of trade-offs on the engineering side, but Violet, let me turn to you a little bit and let's talk about explainable AI a little bit in terms of what's there. And I'm just going to say XAI from now on because saying explainable AI trips me up.
It's a mouthful.
It's a mouthful. It does trip me up. So what is it about explainable AI or XAI, and how are different kinds of XAI expressed to different stakeholders? I mean, if I were somebody looking at a model and looking at something that came out and wondering about the decision, how would it express it to me that I would know?
Yeah, that's a good question. I guess to like backtrack a little bit, I'll just explain what explainable AI
Please.
is. Because a lot of people have different definitions of explainable AI and also explainability. So for our project and also for our discussion, the way we've been thinking about explainable AI is basically that transparency is this big umbrella and explainable AI is one technique under that umbrella. explainable AI referring basically to a subset of different techniques you can use. So techniques like LIME, SHAP, GradCam, these are common ones.
Okay.
But there are a lot of other techniques under the umbrella of transparency. And then another topic is also interpretable AI. So we touched on this earlier. Some people use interpretability and explainability interchangeably, but some people use them to mean different things. So explainable AI are these techniques that you can apply to a model that's not very interpretable, and interpretable or interpretability techniques are about that model itself. And so like a simpler model, some of the earlier kinds of models are more interpretable. So basically, when talking about explainable AI techniques and explainability, there are actually a lot of different ways you can explain model behaviors and outputs, and they can take a lot of different forms as well. So a popular method is to train a surrogate model for your more complex model that can basically mirror its behaviors and then sort of probe that surrogate model to better understand the larger, more complex one. But explainable AI outputs can look a lot of different ways. So in the computer vision space, heat maps are really popular. So basically pointing out like which pixels in the scene were the most important in reaching an output. There are also natural language-based explanations, example-based explanations. So you can really tailor the format of the explanation and the content to the stakeholder that you're working with. A big part of our project also is, so to date, a lot of explainable AI work looks to support developers, which I think makes a lot of sense.
Sure.
Because it can be really helpful as they're working on models to make sure they actually perform the way that they're expected. But I think it's a little more challenging when you're explaining like these kind of complicated AI concepts to end users who may have limited degrees of knowledge about how AI even works. So yeah, there's a lot you can do to craft them to different stakeholders, but there's definitely a lot of work that needs to be done to figure out how you can effectively craft them and communicate explanations to different people.
Sounds really challenging, especially if you've got somebody under time pressure to understand this. Like a decision is coming out and I have to know what to do right away and should trust it. Are you sort of looking at that brand of stakeholder as well to say, how do you get somebody to really understand quickly what's happening?
That's a good question. So the way our project's structured, and I mentioned this in the video, we're working on 2 case studies basically. So our current case study, we're working with a conservation nonprofit called WildMe. Their system, the way it works is the end user inputs an image of an animal that they're researching. They tend to research like populations of animals, and they use this as a replacement for physical tagging. And then the system will provide to them a list of potential matches of who that individual animal might be. So these people, we have to do more to like talk to them, figure out their specific needs, but based on discussions with the customer experience team and the product designers, they have time to review the matches manually and figure out exactly what's going on with the population they're looking at. This is a tool to speed up that process and enable it, but they have time, so there's not that time crunch. So it's not coming into play with our current case study, but starting probably in January or February, we have plans to work on a case study with someone developing a system for the mission space. And the goal there is to kind of untangle some of those questions about what this might look like if you're dealing with a more time-sensitive kind of situation.
Are you still looking for more mission partners in that space?
Yeah, we are. So we're starting to talk to people and trying to figure out what projects might be good to work with. So we're definitely looking for projects in the computer vision space, primarily since that's the case study that we're currently working on, people who feel that they have transparency needs. So.
Okay. So for those of us who are just trying to use these systems right now, any advice on how we can begin to understand, just given the current technology, how to explain the results that we're getting?
That's a good question. So are you talking about as the end user or?
End user, or even as a developer?
Yeah.
I mean, are there things that you're already seeing that we can incorporate either as a developer or an end user that can help get us there?
Yeah. So as an end user, I think it's challenging if you're working with a system that doesn't currently have any transparency mechanisms in place, but you could kind of look online and try to see examples of other models being explained or become more informed about how AI works in general. But there's definitely obstacles to understanding specific systems if they don't have something implemented to help you. So that's a challenge. And I'm hoping that as we build out our methods for AI practitioners to implement explainability and other transparency techniques, we'll see maybe in the DoD space, for example, more people employing these methods. But then on the developer side, there are definitely ways you can get started. There are a lot of resources related to explainable AI techniques, a lot of open source implementations. There can be challenges, I think, in picking up open source software and just applying it to your system, but at least it's a starting place, and I think it can be really useful as you're developing.
I can imagine there's a whole other set of levels of trust as to whether I trust the explanations because they're coming from a place that was open source.
Yeah, that's another good point. You got to make sure that the implementation is accurate.
Yeah, rigorous and robust, and actually does what I think it's going to do, which is a whole different area in explainability, right?
Yeah.
The whole different way it does it. So, Violet, I'm going to come back to you a little bit and talk a little bit in more detail about sort of Anusha. I said Violet. I'm going to Anusha. Anusha, to come back a little bit to the detail that you talked about a little bit with foundation models versus sort of training the child models that are coming out of that. So are you going to extend experiments to the foundation models themselves, or are you just really looking at child models to try to reset the fairness?
So as I kind of discussed in the video, which you guys should all watch online, so we're basically training two different types of foundation models for the experiments that we're running right now. So we have like a performance optimized fairness foundation model, and then a fairness optimized foundation model, and then we're training child models from that. And right now, most of our experiments are focused on the child models because we're really trying to understand that like bias transfer from the foundation to the child models. But also, like right now, most of our experiments have really been focused on just image models or image classification models, but that is also something that we're looking to expand to other types of foundation models, because obviously a lot of the foundation models that are used in practice today are often like language models. And so we are interested in kind of extending the scope of our experiments to these other types of models and like other data modalities. Specifically, we're interested in looking at text models that are being used for like text classification, because I think it's easiest for us to sort of come up with fairness metrics in the context of classification, as opposed to like sort of generating text. It's just harder to like quantify unfairness like in that with those kinds of outputs. But when the model is giving us like a classification output, it's sort of much easier for us to determine if this model is fair or not, and the degree to which it's fair.
So as you get into generative AI, the metrics are likely to get more complicated and more interesting to try to set.
Because they just have to become more complex because the outputs themselves are becoming more complex. And also the results sort of become more subjective. So like, for example, a lot of the generative models that are used today, you can see like biases, like if they're producing images of like faces of people from like minority groups, like people might say that, oh, like the images of Asian people being produced are like sort of very generic, versus like the images of, you know, people from other majority groups are like maybe more unique. And it just becomes much more subjective to kind of evaluate, you know, like whether something is like unique or kind of learning stereotypes.
So it's interesting because, I mean, we often think about minority groups as only sort of coming into minority people or some of these areas. Is it also true that a minority group could be like DoD platforms versus all the cars and trucks in the world, or? Yeah.
I mean, especially like if you're working with data sets with like objects, for example, like there might be for example, if you're working with like, let's say, images of like aircraft, like if you're familiar with like the rare planes data set, and there's like the representation of like civilian aircraft in that data set is huge, and then there's a couple types of military aircraft in there, but they're just much smaller representations. And so you might want to ensure that your model is sort of treating these smaller subgroups fairly, even though they're not really like, you know, corresponding to minority groups in our like population necessarily.
That might be one of those cases where sort of accuracy and fairness could really differ.
Yeah, exactly.
In terms of what's happening in that particular kind of area. Okay, so I'm going to get into a couple of other of the questions and things we have here, but I really do, and Violet, I am going to turn back to you at this point, and really talk about how you're going to, or what advice you might have for practitioners looking to implement transparency mechanisms. So we talked just a minute ago about what they could do today with the existing tools that are out there. But if I'm somebody out there saying, well, I want to develop more transparency or develop more of the explainable AI tools, what can they turn to?
Yeah, so we're in the early stages of our case study. So our plan, we have a lot of open questions related to what you do with explainability software in the long term once you've integrated it into a system. So for example, if you're retraining the deep learning models that your system uses, what's the timeline for retraining explanations or like surrogate models, for example? So those are questions that we have yet to answer, but right now we're in the need finding stage, and I would say we're already learning a lot about what this looks like in practice. So for example, a lot of the papers that we looked at as part of our literature review talked about need finding as mainly being about talking to end users, which I think is super helpful. I think it's a great way to learn more information. It's
Right.
core to design processes. But one thing we've realized is that it's also really important to probe your model and understand what kind of weird or unusual behaviors it's displaying so that you know what might need to be explained. So I would say, yeah, we're already learning a lot about kind of what that process should look like and realizing that needs to be more holistic than how it's been kind of talked about. Another thing is, going into the project, we were thinking, let's just look at explainability techniques.
Right.
But we realized once we looked at wild mies systems that they also had scores that they were showing end users. And they also have kind of some challenges in that they will show outputs for multiple models, and it's up to the user to figure out which model's results to go with. So I would say another piece of advice to AI practitioners is to cast a wider net and not be too prescriptive about what the solution looks like. Not just say, okay, it's going to be explanations, but instead think more broadly about what transparency could look like in the system.
That's really interesting because, as we get into turning this into a more engineering framework and a real way of doing the trade-offs, it sounds like you're going to be really extracting a lot more detail and substance in what really you have to trade off with regard to explainability, with regard to interpretability, really sort of understanding what the developer has to face and then what the user has to do in terms of their visuals and what they can see.
Mm-hmm.
Would that sound about right?
Yeah, definitely. There are a lot of trade-offs that you're dealing with as a developer. So for example, with the wild mies systems, they're switching to these models that can handle multi-species instead of one model for each species. And this leads to improvements in performance, but it makes their models less interpretable. And so that's a trade-off that they're trying to grapple with, just as an example.
Excellent. So Anusha, we have a question coming out of from our live stream that's coming in from Dan on YouTube. How do you determine if something is fair? Do the humans have to monitor that? Is there an algorithm?
Sure, yeah. So for our experiments right now, as I kind of mentioned, we're focusing on this disparity of accuracy with the minority group versus the rest of the population. And in order to compute that, we're relying on these secondary labels in the data set. So basically, for the experiments we're running, it's a data set that is classifying people based on their role, for example, astronaut, judge, cowboy, basketball player, and then the secondary labels are information that encodes stuff about their race or through their skin tone, or maybe their the gender presentation or their age. And so we're basically using those secondary labels and then separating out different chunks of the input data based on those secondary labels, and then separately computing accuracy metrics on that subgroup versus the rest of the population.
How large are these data sets? Are they actually significantly large enough to give you the results you need?
Yeah, so that's actually one of the struggles that we've had is finding large data sets that contain these secondary labels. So the data set we're using right now is about 50,000 samples, which is actually pretty small.
Seems small.
Yeah, compared to a lot of the data sets for these large foundational models. But yeah, that's definitely something that we're looking for other data sets to use. So if anyone out there has suggestions for other image classification data sets that contain these secondary labels that are significantly larger, we're very interested in hearing that.
That's excellent. So in all of these, especially with the sort of the size of the data sets and the results that you're going to get out of this, do you think those results will be definitive in terms of understanding the nature of the fairness problem, or do you think this is just the first stage in getting into that?
Yeah, so I think right now our experiments are pretty much focused on CNN-based architectures, but obviously that's not the case. Many foundation models used right now are transformer-based architectures, and so we are interested in seeing how these results will sort of transfer to these other models. There's some literature out there right now about sort of the suitability of transformer-based architectures for transfer learning, and the results that other people have published have kind of shown that transformer-based architectures are sort of equivalent feature extractors as CNNs for transfer learning, and they actually maybe even slightly better performance in some situations. And so we expect that if we can quantify bias that's being transferred from the foundation models to child models with the CNN architectures, we expect that we could use similar methods for these transformer-based architectures as well, and that the results would be somewhat similar. But in my presentation that's on YouTube, I kind of talked about the first series of experiments that we ran to kind of understand the transfer of stereotypical examples
Yes.
from the foundation of child models. And I think some of those results might sort of vary between the CNN-based architectures and the transformer architectures, because the transformer architectures don't really have the same like inductive bias as like stacked convolutional layers have. So some of our results in terms of like quantifying bias transfer as we're varying like the layers that are frozen or unfrozen during fine tuning might not exactly transfer between the two different architectures, because fine tuning practices are kind of different between them. But I do think that our results should be somewhat general, and we are actually interested in running some experiments with vision transformers.
Given your experience, do you think it's even possible to train a foundation model that's sort of free of bias in all the dimensions that we're sort of looking at today?
Yeah, so I mean, technically, you can't ever train a model that's free of bias, because you need bias in order to make meaningful decisions. And so I don't think it's possible to train a foundation model that's completely free of bias. But our results are sort of just meant to inform kind of best practices, so that people can understand like whether it's really important to start with a foundation model that is fair by a certain metric that you care about, or whether you should try to just start with like a foundation model that's sort of performance optimized. And then when you're doing your fine tuning, that's sort of when you need to be really careful about the metric that you're selecting. And like the performance based on that specific fairness
That's
metric.
a great point.
But,
Great point. Yeah, one more follow-up from Dan online.
Sure.
And aren't there privacy issues in terms of what you're trying to do here? Are you concerned about privacy issues?
Yeah, so in terms of collecting secondary labels with the data set, so we definitely are. And a lot of the data sets that are like public right now that contain secondary labels have a bunch of, you basically have to like sign off on these agreements saying that you won't use these secondary labels for a specific classification. So like you won't try to classify the images based on race, or that you won't specifically try to like diminish the performance on a specific like subgroup. But yeah, that's definitely one of the big stumbling blocks, it seems like, with collecting these secondary labels for.
Okay. Well, we only have a couple of minutes left, but I'd really like to hear where this goes next. I know you're right in the middle of a 2-year project that's coming right into a second year where you're going to begin to get more mission focus on your data. But what comes next in this research?
Yeah, so our next step is really to, kind of close out this case study that we're currently working on. We plan to do that by April, and our goal is to just document the whole process and get as many insights from it as possible. And then we want to apply that same process to a project in the mission space, and the goal there is to figure out which pieces are generalizable and which ones are really specific to process or a specific AI practitioner team or system, which I think really has parallels with what Anusha is doing, because you have to start somewhere. You have to start with one example and really kind of do a deep dive into how that works. And then the challenge, but also some of the most exciting, I think, aspects of the work is when you pick up those insights and you apply them somewhere else.
Absolutely. And same question, what are the next stages of your project? You're in the middle of a 2-year one as well?
Yeah, so we're continuing the experiments to sort of quantify specifically the bias that's being transferred from foundation to child models, and our goal is to expand to other architectures and other data modalities, basically, over the next couple months, so that we can get general results.
So finally, I mean, the two of you work relatively closely together here at the SEI.
Yeah.
What do you think you're going to learn from each other's work?
Okay, I guess I can go first. I think fairness can. There's a lot of definitely overlap between, I think, fairness and explainability, and I think it could be one of the dimensions of explainability. Almost like that might be one of the ways you want to understand the behavior of your models in like the context of fairness over certain minority groups. So I think there's definitely a lot of overlap, and then understanding like the process that people are using to sort of incorporate explainability, interpretability techniques in their systems, I think would be very useful for me as I'm like sort of developing these like new methods to sort of quantify bias transfer and understand how I can get those results into the hands of people.
Very insightful.
Yeah.
Yeah, definitely. I agree. I think you can use explainability techniques to help understand the fairness of your model, and I think that's a worthwhile goal. And I also think your work is really rigorous, and I feel like working on these methods that are quantitatively backed is a really cool way to approach it. And I think moving forward with the explainability work, we're going to be running surveys to get as an evaluation kind of component, but I think basically those techniques, I would apply them to explainability problems moving forward. We're kind of in the first step, but there's definitely a lot more moving forward. So they're complementary.
Well, this is great. I mean, I think both of these areas of research are real key steps in getting us closer to doing rigorous engineering of these various AI systems and really understanding the trade-offs. I really do hope that all of you who are watching, or either live or a recorded version of this, will turn to their very well recorded research that's out there to get some of the details of what's going on here. And please reach out through info@sei.cmu.edu to ask questions, to really get into their research. You can tell more data is needed, more mission partners are needed, more areas of interaction and collaboration will only help all of us do better in a situation like this. Thank you both very much. We're going to be taking another short break as we get a little bit reset into our next panel. In the meantime, please watch the intro videos for the next panelists that will be coming up. And once again, we'll see you in a couple of minutes. Thank you very much.
Hello, my name is Jeffrey Hansen. I am a machine learning research scientist at the Software Engineering Institute. While machine learning models can be very powerful, they are known to be brittle when presented with data outside their training distribution. The transition from inputs where a model performs well to inputs where a model performs poorly can often be abrupt and dramatic in a sort of digital cliff effect. Potential causes for this falling off the cliff can include data drift, concept drift, or simply deploying an operational system in a new environment. Complicating this problem, models often do not know when they are wrong, leading potential disaster as systems blindly continue over the cliff. To address this issue, we have developed Portend, a set of tools that enable data scientists to build monitoring and alerting agents that detect and respond to data drift or out-of-distribution data in ML systems. These tools include a library of drift inducers, a set of monitoring techniques that enable data scientists to synthetically generate drifted test data, and then apply those monitoring techniques to produce targeted drift detectors for a system. This enables those systems to take alternative actions in response to reduced model accuracy or be flagged for retraining. Check out our talk to learn more about Portend and how successful it has been in practice with real-world data. Then bring your questions to our live event on November 8th.
Hello, I'm Gabe Moreno, Principal Researcher at the Software Engineering Institute. The Department of Defense must be able to deploy new capability with speed and confidence as missions and environments change. As systems increase in scale and needed capability evolves more rapidly, achieving speed with confidence becomes more difficult because software assurance delays deployment. We are developing formal arguments for large-scale assurance to both strengthen and speed up software assurance of rapidly evolving large-scale systems. We developed a model that supports reusing and integrating assurance analysis and results with different levels of formality. It ensures that the combination has a single interpretation that can be automated. And it uses runtime monitoring to detect whether system behavior conforms to the assurance argument. We demonstrate the model using a humanitarian mission carried out autonomously by a UAV to deliver life-saving supplies in a disaster zone. Check out our talk to learn more about using formal arguments for large-scale assurance and how model logic and scientific machine learning are key ingredients for achieving speedy deployment with confidence. Then, bring your questions to our live event on November 8th.
Hello, my name is Jeffrey Hansen. I am a machine learning research scientist at the Software Engineering Institute. While machine learning models can be very powerful, they are known to be brittle when presented with data outside their training distribution. The transition from inputs where a model performs well to inputs where a model performs poorly can often be abrupt and dramatic in a sort of digital cliff effect. Potential causes for this falling off the cliff can include data drift, concept drift, or simply deploying an operational system in a new environment. Complicating this problem, models often do not know when they are wrong, leading potential disaster as systems blindly continue over the cliff. To address this issue, we have developed Portend, a set of tools that enable data scientists to build monitoring and alerting agents that detect and respond to data drift or out-of-distribution data in ML systems. These tools include a library of drift inducers, a set of monitoring techniques that enable data scientists to synthetically generate drifted test data, and then apply those monitoring techniques to produce targeted drift detectors for a system. This enables those systems to take alternative actions in response to reduced model accuracy or be flagged for retraining. Check out our talk to learn more about Portend and how successful it has been in practice with real-world data. Then bring your questions to our live event on November 8th.
Hello, I'm Gabe Moreno, Principal Researcher at the Software Engineering Institute. The Department of Defense must be able to deploy new capability with speed and confidence as missions and environments change. As systems increase in scale and needed capability evolves more rapidly, achieving speed with confidence becomes more difficult because software assurance delays deployment. We are developing formal arguments for large-scale assurance to both strengthen and speed up software assurance of rapidly evolving large-scale systems. We developed a model that supports reusing and integrating assurance analysis and results with different levels of formality. It ensures that the combination has a single interpretation that can be automated. And it uses runtime monitoring to detect whether system behavior conforms to the assurance argument. We demonstrate the model using a humanitarian mission carried out autonomously by a UAV to deliver life-saving supplies in a disaster zone. Check out our talk to learn more about using formal arguments for large-scale assurance and how model logic and scientific machine learning are key ingredients for achieving speedy deployment with confidence. Then, bring your questions to our live event on November 8th.
Welcome back. I hope you enjoyed the promo videos that are coming up. We have another excellent panel that's coming forward at this point to talk a little bit in more detail about a couple of the other issues surrounding both the AI areas and maybe more importantly talking about certification and really trying to understand how do we get these systems trusted in a way that we can get them out there and deployed. So we've got two excellent panelists that are with me. I'm going to ask them to introduce themselves. And Jeff, I'll start with you.
Hello. Yes, so my name is Jeffrey Hansen. I'm a research machine learning scientist here at the Software Engineering Institute. I'm part of the Software Solutions Division. I've been here for, at least 10 years now. And I've done quite a large range of different tasks here, ranging from like working wireless networking, resource management, real-time systems, and now I've been working on machine learning the past few years.
Thank you, thank you. And Gabe Moreno was not able to be with us here today, but we have him here as a Max Headroom stand-in. Really appreciate that you're here. And Gabe, introduce yourself, please.
Yes, hello. I'm Gabe Moreno. I'm a principal researcher at the SEI. I've been at the SEI for about 20 years now. I came to Pittsburgh originally to do my master's in software engineering at Carnegie Mellon. And then I stayed and then did my PhD in software engineering, so been here in the city for a while. My main area of research is on self-adaptive systems and in how to formally verify some of the qualities that we want these systems to have.
That's great. So Gabe, staying with you for just a minute, for the project that you're currently working on, what would you say are the key research questions and issues that you're dealing with right now on this research project?
Yeah, so what we are trying to do is to remove some of the barriers that there are to assure systems with speed. And some of the issues are that there's no way to reuse assurance results, and also it's difficult to combine different assurance results that have different levels of formality. So we may have something that is very formal, let's say based on model checking or theorem-based proof properties, and we may have some other informal forms of assurance, maybe just some testing or inspection. And what we want to do is to be able to put them together in a formal argument that can be evaluated automatically. So the key research question is, what are the techniques that we can use, the formalisms that we can use to incorporate in a single formal argument analysis results or assurance results that have different levels of formality. That's the main question we are dealing with. And in addition to that, later on is how can we check that the runtime behavior of the system conforms to that assurance argument. So if the assurance argument says that property X holds, we want to make sure that that happens at runtime too.
So Gabe, isn't this really just a factor of saying, I have requirements, I'll test those requirements. If they pass their test, the system's good to go? Where are you really looking at beyond sort of the testability of systems?
Yeah, so the idea is, let's say we have a claim that the system, let's say, should be able to complete a mission safely. Now that claim can be decomposed in subclaims, and then for each of them, maybe we have different forms of analysis that can be used to prove that claim. So maybe if there's a timing requirement for something, we can use scheduling theory and the related analysis to make sure that tasks meet their deadlines, and that will be one part of the argument that we have there. But we may have other qualities that may require other forms of analysis, and for some properties we may resort to other forms of evidence. Let's say maybe it's just inspection. So the idea is to have this argument where we can put all of these things together and evaluate them in this combined way, and making sure that that top claim that we were interested in is satisfied or holds. So it's not just testing, it's all the analysis and verification that goes to show that the system will have that property.
Thanks, Gabe. So that's much more rigorous as an approach to this kind of thing. Is scalability a research question as part of this? Because historically, I can remember a lot of formal methods techniques that just didn't scale to the size and complexity of the systems that we have now.
Yeah, so in our notion of this formal assurance argument, what we are doing is taking the details of the analysis as actually not looking at them. The analysis for us is a black box, but what we are considering are all the assumptions that the analysis made to provide that result, a given result. So for example, in the case of real-time scheduling, if we are using rate monotonic analysis, one assumption is that the tasks have rate monotonic priorities, and the operating system is configured to do fixed priority scheduling. With that, what we do is to put that in that formal argument, so that we can prove that claim and make sure that the results of the analysis hold without having to contemplate all the details of the analysis. And in that way, because we're just dealing with the assumptions and the result of the analysis, we have this modularity that will help us with the scalability.
That's much more clear. Thank you. I can understand that. So Jeff, what are the key research areas within your project that you have right now, Portend, and where is it that you're really focused there?
So we are also kind of like very interested in AI insurance, and that's kind of the whole focus of our project. Looking at ways to make AI safer. We all know that AI models can do spectacular things, but they can also fail spectacularly as well. And one thing we've noticed is often they'll just go happily off producing incorrect answers, and the system can't handle it and will often fail as a result. So we're trying to find ways to put up guardrails to keep the system safe and avoid going off the edge of its effective area, as we say. So I guess the key question we're asking is, what can we do to make AI safer? What can we do to prevent AI from running amok and getting out of its comfort zone?
Are there specific either metrics or limits or something with regard to the research on the guardrails that you're shooting for? How good do these need to be?
Well, that's going to, of course, depend on the application that you're doing. It's kind of up to the the system designer to decide sort of which areas they want. If you've seen the presentation we resolved, it's based on creating these drifters that create drift induction, and so you'd probably want to focus on creating drift inducers that are specific to whatever problem area you're looking at. If I'm a drone that's going over that might go into a flooded area, might go into areas of weather, I might want to induce flooding or fog. If I'm going into war-torn areas, I might want to look at building damage and so forth, and using that sort of drift induction.
Well, we have a related question coming in from online from Stanley. Are there significant concerns with confusing adversarial perturbed data with odd data? Are there ways in which we can distinguish this sort of odd data and the adversarial data, and sort of how should they be respectively distinguished?
That's a very good question. I can't say that I have an answer offhand. In my mind, I would think that could be, in fact, like another type of drift inducer that we can produce that creates adversarial data. We look for correlations between the amount, how strongly induced the adversarial effect versus different effects in the model, and try to find metrics that can help us detect that.
This sounds a little like what we historically have done with fuzzers, where we've essentially tried to create various kinds of fuzz data and various things that would drift the results. Now this is in much simpler kinds of systems.
Yes.
But is it kind of like that, and can we associate that with adversarial data?
I think that's a very good analogy. Yes.
Okay, that sounds really great. So Gabe, I want to turn back to you for just a minute. Was there some finding in this project that led you to change the solution approach you had originally envisioned? Because we went back a long way talking about this project, and I think some of maybe the original assumptions have modified or changed a little bit.
Yeah, so one of the things we had in mind was, remember, the idea is to be able to combine different analysis results. Some of them are very formal, some of them are informal. We had this idea that combining informal results was sort of like the easy part of the task, and the main focus was on how to protect the formal guarantees from being affected by the informal parts of the argument. Now, then, as we were working on the project, we realized that it wasn't that easy to just combine informal results. One of the techniques we thought we were going to be able to use is something that comes from information security, which is the notion of tainting. If you look at an assurance argument, it generally looks like a tree, so you have a claim at the top, and that gets decomposed into subclaims, analysis that support the claim, and so on. So it looks like a tree, and the idea was, well, if we think of an informal argument being sort of like taint that could taint a formal result, then we could propagate that taint. But then we realized that combining informal arguments was not always feasible to do, at least not in a principled way. So this notion of if I have two inputs that are tainted, I just get an output that is tainted, didn't work. So when we started looking at the use of modal logic and the inference rules that we had to use for that, we realized and we came up with rules for when we can combine informal results. One example that was in the talk is, suppose that we want to prove the claim that the drone is able to complete the mission safely and on time, and both of that gets decomposed into the safety part and in the timeliness part. And then for both of them, we have informal analysis in this case. Let's say some form of simulation for the timeliness part and some form of testing for the safety. Now, suppose that the safety part was done with the drone flying at low speed, and the timeliness part was done with the drone flying at high speed. Well, I cannot just say that it's possible to complete the mission safely and on time, because there was that inconsistency. So in that case, even though we are combining informal results, we cannot just put them together. So that was one realization that made us change a little bit the direction during the project.
Gabe, does this also help us maybe change the way that we do the analysis on various claims in order to synchronize the worlds better so they might combine to achieve our claim?
Yeah, good point. Exactly something that we are considering now that we have this foundation is that we may have sort of like a degree between something that is just possible and something that is valid, meaning that it holds in every possible case. And the idea is that we could have a notion of a claim that is possible in a number of worlds, not just in a single world. So the more worlds we have shown that claim to hold in, we can say that the stronger that claim is. But now when we are combining them, the resulting claim will be possible at the intersection of their respective worlds. So like you were saying, we can craft the analysis that we do and decide what these analysis worlds will be so that we can maximize the strength of the resulting claim.
That's really great. So Jeff, I want to turn back to you for a little bit. Can you talk first of all a little bit more about the portion of the project where you're building a monitor as opposed to doing the work during development in order to understand whether or not a model is drifting?
Well, I mean, the monitor has, both the design time and the runtime aspects to it. So, at the development time, the data scientist is looking at data, and basically the idea is to take, start with a clean data set, gradually induce drift into that data set, look for how the model reacts to it, and then you can see, since you're inducing the drift yourself, you know how much drift is in it,
right.
And so you know what the error is, and so you have this error correlation. You like to look for internal cues in the model that correlate with that amount of error, and then that can get deployed as a model, as a monitor that gets deployed in the system, and so it will then in the live system be looking at how that measure changes, and when it sees that measure increase above a threshold, it will say, hey, something's wrong, it's time to replan.
So in the previous panel we talked a lot about explainable AI. It sounds a little to me like the runtime monitor is helping to explain a little bit better the results that you're seeing.
Yes, I think that there is a similarity there. We're focusing on the question of is the model possibly going wrong or untrustworthy, and trying to make metrics for that are easy to generate and respond to.
So how do you express that to someone who's maybe using a deployed model? Someone who is maybe looking at an object detection model and it is drifting away because the objects have changed.
Yeah.
So how would you reflect that to an operator, to somebody who is using the model?
So I might say that this metric, you can think of it as a confidence level. Like, if I have a low score, we're saying, there's usually these are like a different score. So
Okay.
so a low score might mean that everything is good. As that score goes up, that's more and more an indication of that there could be some problem with the model. Maybe you should be less trusting of the outputs you're getting.
Let's get a little more specific on how drifters works. How does the flood drifter work?
Different drifters, I'm going to generalize that a little bit. So one of the nice things about Portend is it has a very clean interface with how you can write drifters. So as long as you write to that API, you can do pretty much anything you want to. Some drifters, like fog, are very algorithmic. They simply do sort of standard image manipulation type techniques, but some, like the flood industry you're talking, those are actually machine learning models themselves. So the flood inducer in particular, we've found some research that basically image to height transformations. They'll be trained on overhead imagery registered with LiDAR imagery.
Ah, okay.
And so by doing that, you can build a model that can take, standard overhead imagery and predict what the LiDAR model of that image is. And then by recomposing that LiDAR image with the original image, you can create the flooded data.
So literally wash out the lower levels of the
Literally
image.
wash out,
Literally
yes.
wash out those
Yep.
details.
Yep, exactly.
That are sort of in there. That's really great. And the runtime monitoring that you sort of consist with that would then be able to somehow give you an indication that the model wasn't trained this way.
Yes.
And what you're getting is not trustworthy.
That's exactly correct.
So Gabe, turning back to you, because this is a little similar to what you're thinking about with runtime monitoring as well, right? When you get out of the range of the claims and the arguments. Can you talk a little bit about how the runtime monitor works?
Yeah, so the idea is that we have the assurance argument and we have some claims that have been proven either by some formal analysis or testing or other methods. And the argument says that claim holds. Now, we want to make sure that the claim holds because there are different reasons for which it may not hold anymore. Maybe some incorrect assumptions were done when the argument was created. Of course, the argument is based on models, which are abstractions. So maybe there's something that doesn't represent really well the reality. And the other aspect is that things change. Maybe now the system is deployed in a different environment, and now that property doesn't hold. But the thing is that we want to detect that that's happening. And we have started, the work we did in FALSA was in two different areas of monitoring. One was for linear temporal logic properties. Mm-hmm. So, for example, a claim in our example with the drone delivering supplies is that the supplies should never be dropped before reaching the destination. So that is something that it's proven in the argument with some model checking that perhaps was done offline, but then the monitoring checks just events that are emitted by the software. They can come from a log file, and what we are doing is based on the linear temporal logic property that should hold, we generate a state machine that keeps track of the events that are being emitted and detects if the property is violated. So that's one area. The other area is for physical correctness, and this one is really important because most or many DoD systems are cyrophysical systems, meaning that they interact with the physical environment, and their correctness implies being able to move correctly through the physical environment. And the physical correctness is, if that is not right, something is wrong with the physical behavior of the system. That's sort of like a macro indicator of other things not being right. Think that for a drone to be able to fly correctly the intended trajectory, many things have to go right. The reading of the sensors, the timing on when the sensors are read, the timing of when the actuation is issued, and so on. So if we can detect that the drone is not behaving physically as it should, that's an indicator of other things that might be wrong. And the approach we use for this physical correctness monitoring comes from the area of scientific machine learning. This is an area of machine learning that uses scientific principles that comes from physics. So they are expressed in differential equations. And usually a deep neural network is approximating a function. Well, in a physics-informed neural network, the neural network is approximating the solution to a differential equation. Now, in particular, in FALSTA, what we used was something called operator networks, or depot nets. And in this case, what is learned is the mapping between two function spaces. And in the particular case of our example for the drone, the mapping was from control functions that are the actions applied to the physical drone, a mapping from that function space to the trajectories of the drone. So given a control, we can compute the trajectory. Now, with the depot net, we are able to do that in real time, but the important thing is that we can do that using the non-linear behavior of the system. This is an advantage to other approaches normally used, that for timing reasons, they need to use a linearized version of the dynamics of the system. But with depot nets, we are able to use the non-linear dynamics. So that's an advantage for that kind of monitoring.
That's really quite an advantage, especially since with the physics-informed portions of it, you're actually reflecting reality. And you can compare that to the basically the approximations that are coming out of the machine learning as well, right? I mean, in terms of knowing whether they're going to match up to the dynamic equations that you're actually using from the physics-informed side.
Yeah, exactly. So we have two parts of scientific ML that we can use. One is to give, if we get runtime data for the drone, from the drone, we can use physics-informed neural networks to estimate the right parameters and adjust the parameters that were in the assurance argument so that it better reflects that reality. But the other thing is this really fast checking that we can do using the nonlinear dynamics, and that's really an advantage because the flight controllers are based on a linearization of the dynamics. So by predicting a more accurate behavior, we can detect problems even before they happen.
Great. So Jeff, this actually brings up a whole other area. Because when we start talking about all of this other data and sensors that comes in, this goes way beyond sort of the initial versions of drift that you're talking about with image data.
Yes.
So how difficult is it to write drifters for some of these other sensor environments, for maybe even language models, for all of the things that we want to think about that are not images?
So, I mean, that's also a good question. I mean, Portend, evolved from a previous project that was looking at mainly time series data and doing, some of the sort of moving in the direction we are going in. So the system itself is already sort of designed to work with other types of data.
Yeah. So you talked about the APIs that link directly in terms of the drift data. How generalizable are these APIs? What kinds of drift data can they actually accept?
So I mean, the basics of, it's basically anything that you can represent as a tensor, it will transform that tensor to a new tensor. And
so however you represent it with regard to the various parameters of the system, that's what you can use for the drift.
That's correct.
So that sounds very much applicable to almost all the new transformer models and everything else that we're seeing out there. Are you going to be moving in that direction?
We may try to go I'm not sure if we'll do it within the Portend project itself. We're working actually very closely with Gabe and his project, and we're hoping to actually deploy some of the monitors that we generate in sort of live experiments on an actual drone.
So you are working a little bit, you know what Gabe is doing, you know the
Yeah.
kinds of things that are happening. Is there anything in your project that you're learning from Gabe's project?
Oh yeah, I mean we're learning a lot about different I mean we've been using some of the algorithms that he's using. There's been a lot of crosstalk and trying to figure out what models are best for doing the localization that he's doing in his project. Which ones are easiest to get parameters. We started out with an older algorithm that it was very brittle, very hard to use, very hard to find metrics that we could correlate with error, and then we since moved to another easier to use model.
That's great. And Gabe, I mean, just in terms of where portend is, in terms of drift and looking at the models that way, can you incorporate that in the claims and the ways that you're thinking about this?
Yeah, I think that's a great idea, and that's where the connection would be, because it's a concern when we have components that are based on machine learning on the system, right? Like Jeff was saying, and we want to know when they are not working well. So part of what we would have in the assurance argument is the argument that says whenever we should not trust the output of this learning-enabled component, we will do something else. Either we will ignore it, we will switch to another sensor, and so on. So that becomes part of the argument. But then the runtime part, the monitor, is what actually we have in the system to realize that. So yeah, they are complementary in that way.
So in both of your projects, one of the things that I really see is a strong quantitative ability to get into ATO or to get into certification of systems that are out there. Are these pieces that we expect to see incorporated into acquisition programs, into major efforts that are going to be happening within the DoD or even outside of the DoD?
Yeah, I mean we're very interested in that. We have some people we're talking to.
Great. Gabe, same with you?
The same. Assurance is critical for many systems. DoD needs to deploy new capability, and that capability needs to be assured. So if we can help speeding up the assurance of those systems, this is a technique that will help with that.
That's fantastic. Well, I want to thank you both for being here on the panel and helping our audience really put your work in context and really sort of put it into place. I really do ask all of you who are watching and those who see this as a recorded, please go to their individual presentations on the research. They're very detailed and have a lot of additional information than what we were able to cover here. And please, if you have any questions at all or want to reach out to these individuals or the folks that they're working with on the back end, info@sei.cmu.edu is the place to reach out and reach out to them and come into where that's going to happen. So again, thank you very much for listening to this presentation. We hope that this helped you understand a little bit better on this side. We're going to take a few minutes break while we get the next panel set up, and during the time, please enjoy the promo videos of the next panel that'll be coming up. Thank you all for watching. See you soon.
Hello, my name is Will Kleber. I am leading a project on detection of malicious code using static taint analysis. Malicious code can be inserted by an adversary who attacks a software supply chain via network intrusion, such as in the SolarWinds incident of 2020. Our goal in this project is to improve the DoD's ability to detect such malicious code. Currently, it is impractical to ensure that significant amounts of code is free from malicious code. Existing automated tools produce way too many false alarms, and manual analysis is difficult, time-consuming, and expensive. We aim to remedy this with the tool that we are developing. Our goal for the tool is to produce output that concisely characterizes the potentially malicious behaviors of the codebase so that a human analyst can quickly and accurately determine whether their behavior is benign or malicious. Our tool will detect exfiltration of sensitive information, as well as time bombs, logic bombs, remote access trojans, and so forth. To do this, we will identify the conditions under which sensitive flows and sensitive operations happen, especially those conditions that are indicative of malicious code. Our aim is to provide enough information to enable an analyst to quickly dismiss almost all false alarms without needing to manually examine the source code or the decompiled binary. If you are interested in our tool, please get in touch with us.
Hello, I'm Justin Novak. I'm a senior cybersecurity operations researcher at the Software Engineering Institute. My main area of research is in security operations and the development of security operations centers, or SOCs. SOCs are organizations that help agencies, businesses, or other government entities and private entities improve their cybersecurity posture and their cybersecurity operations. These organizations are becoming of increased importance, but they're also becoming increasingly difficult to deploy in terms of the time needed and the expense associated with developing a SOC. That's because there's increasing specialization both in cybersecurity and in general, and with SOCs specifically. We're hoping to solve some of those problems in terms of the expense and the time required to deploy a SOC by doing new research in understanding how experts turn their knowledge into a functional SOC capability. By capturing that knowledge and putting it into a tool that can be accessed by any organization developing and deploying a SOC, we hope to reduce the time and the costs associated with building these critical organizations, both for government and non-government clients. I hope if you're interested in this, you'll take a look at my full presentation and join us at the live event on November 8th so you can learn more about security operations centers and the work that we do at the SEI.
Hi, I'm David Swoboda, a software security engineer in the SEI's Secure Coding team. Software vulnerabilities are a major threat to our nation's mission-critical systems. We can use static analysis to find exploitable flaws in source code, but these static analysis alerts must be audited manually to distinguish genuine vulnerabilities, that is, true positives, from false positives. However, most code bases generate too many static analysis alerts to audit them all manually. And even if we knew which alerts are true positives, there are still too many alerts to repair them all manually. In a recent internal code analysis, we discovered that auditing all alerts generated for the average C or C++ codebase and repairing the true positives would take 3.43 person-years. That's a lot of effort. Our goal is to automatically repair at least 80% of each security-relevant defect category of static analysis alerts. We handle false positives by repairing them, just like the true positives. Our code repairs are intended to preserve soundness and eliminate alerts if the code is reanalyzed. If you're interested in learning more about our research and how we can help your organization handle the deluge of static analysis alerts, watch my research review presentation or reach out to us at info@sei.cmu.edu.
Welcome back to the 2023 Software Engineering Institute's Research Review. I have a great panel here, and I know the topic area is going to be of significant interest because we're going to get into some of the very specific trustworthy and cyber issues around the areas of cyber engineering, software engineering, and that element of what we're going on. So we have three great projects to begin to dig into and talk about with regard to the cybersecurity portion of this. And as before, I'm going to go around and ask each of our PIs to introduce themselves so you get to know them a little bit. David, let's start with you.
Hi, I'm David Swoboda. I've been a software security engineer for CERT since 2007. It's been a long time. So I was actually instrumental in helping to build the CERT secure coding standards for C, C++, Java, and Perl. And as you might guess, my focus study is software security and trying to raise the level of security of all the software that's out there. So this project is taking a more active role in raising the security by actually repairing code.
Will.
Hello, I'm Will Kleber. I've worked at the SEI for about 10 years now. My research has focused mostly on static analysis to detect vulnerabilities as well as detecting malicious code, as well as I've also done some work on automated repair of code to fix vulnerabilities, especially memory safety vulnerabilities. Before I came to SEI, I did graduate work. I did work at graduate school in formal verification of software, in particular working on quantified Boolean formulas.
Oh, great. Thanks, Will. Justin.
Sure. My name is Justin Novak. I'm a senior cybersecurity operations researcher here at the SEI. I just started my 8th year at the SEI, actually. Before that, I started off life as an analyst at the National Threat Operations Center at the NSA. So I have a background kind of working in operations centers. And since I've been at the SEI, a lot of my research and work has focused in the area of incident response, security operations, and so forth. So that's kind of what I'm into now, and looking forward to talking about that more.
That's great. Justin, let's stay on you for just a minute. Can you talk to me a little bit about, in your current project, what your key research questions and areas are?
Sure. So what we're looking at doing is trying to build a knowledge base around security operations. We're trying to understand really what goes into building a security operations center in terms of the people, the processes, and technologies, and then how can we take that knowledge and use it to develop a process that is repeatable for building these types of operation centers and building those teams so that we can make doing so easier in order to enable organizations to just better improve their security and improve their security operations and secure their networks better.
That sounds great. So there's a lot of consultants in this area. There's a lot of books that have been written around this. When you talk about a repeatable process, can you go into a little bit more detail? What does it take to create a process like this that's repeatable when every SOC is different?
That's a great question, and that's really the core of the matter. We've seen other places that have tried to do something where the SOC itself, the build, is just a repeat. It's a copy and paste type of SOC in the box or a CSIRT in the box, and that doesn't work. When we see that tried, we see a lot of failures or organizations that can't really fulfill a mission. That's because the mission is different from one organization to the next. So you might have one mission that says we're going to fulfill a certain set of services, and a different organization might have a mission that calls for a separate set of services. Also, the organizations themselves are different. They're different in size, they're different in scale, they're different in capability, they're different in the amount of budget that they have available to achieve their goals. So instead of developing just a SOC that you can copy and paste, you have a process that you go through to develop a SOC that starts with asking, what is your mission? What services do you want to offer? What is your budget? What are some of your specific needs? How big is your organization? All these other questions. So while that stuff is repeatable, you can go through the process, you have to have a lot of knowledge and expertise and experience to be able to answer all of those questions correctly and to get to a solution that can really meet that need and help you fulfill the mission for your SOC. So what you have to do to make this a repeatable process is to gather all of that knowledge and put it together in one place that can easily be accessed. And that's what we're trying to do.
That sounds great. Is there a piece of this research question that talks about validating what you have in terms of whether or not what you have are the right kinds of things to help facilitate a SOC creation?
Yeah, so at the core of our research and at the core of what we're doing is asking, what would an expert do? So we're looking at developing an expert system that will help with this process, but it's really about tapping into that expert knowledge. So we have to go out and identify who are those people who have been working in the field, who have developed multiple SOCs or multiple incident response teams. And then how do we compare that to like industry best standards, industry best practices, and things like that?
That's great. So Will, let's go back and talk a little bit more about the key research questions in your current project.
Right. So the main goal that my project is trying to address is to detect malicious code that is embedded inside otherwise benign code. Now, the background is, let's say that software is being developed by a contractor, and maybe that contractor suffers a network breach, or maybe there's a malicious insider who injects a little bit of malicious code into an otherwise benign code base. And we want to be able to detect that malicious code before it is put into use. So we are trying to do that with static information flow analysis. So that is the research that we're trying to do, is to develop a technique for, with high confidence, being able to detect such malicious code.
So Will, there's a lot of static analysis tools out there right now. What's the problem with just using the existing tools?
Right. So there's a lot of static analysis tools that are focused on detecting vulnerabilities. And so we are not trying to replicate that. We are trying to look specifically for code that was maliciously inserted, which is different than vulnerabilities, because with vulnerability, it's often the case of like undefined behavior, like kind of out of bounds memory accesses, things like that, where there's where it's pretty clear that this really is a vulnerability. You can like formally verify that, yes, this is absolutely a vulnerability. But the difference with malicious code is that there really isn't such an objective standard for whether it's malicious or not. For example, maybe you have a program that reads data from your microphone and sends it to the network. Is that malicious or not? Well, for some programs, it would definitely be malicious, but you have other programs, like teleconferencing programs, where that would be desired. So that is one key difference between what we're looking at versus what static analysis for vulnerabilities are looking at.
That's great. Do you have a specific piece of malware as an example that sort of exemplifies what you're trying to find?
Right, sure, yes, definitely. So one recent piece of malware that we would want to be able to find is the SolarWinds Orion, that piece of malware that was inserted. So with that malware, there was actually a network intrusion into the company that produced the software, and they inserted malware into the build process of the SolarWinds Orion code. So even if you looked at the source code, you wouldn't find that malware because it got injected during the compromised build process. So yes.
Very complicated structure that you're trying to go after with this. Okay. So David, let's go back into your project. So you're looking more at the what can we do once this has been identified, yes?
Right.
So can you talk a little bit about your key research issues?
Right. So my key research issues ultimately derived from my pain points in my last work, which was mostly looking at code to identify what vulnerabilities there were in it. Here's 1,000 lines of code. Are there any null pointer vulnerabilities in it? Well, the tool says there's null pointer vulnerabilities in line 10, 20, and 30. Are those all true or all false? And there's 17 more to look at. And it gets overwhelming after a while. So the point of the repair project is to identify categories such as null pointer vulnerabilities. I looked at those and I said, I could spend an hour reviewing each one, or we could just put a null check in front of each one and be done with it. So the argument is that these things are easier to repair than they are to audit. And so why go through the auditing expense when you can just slap a null check in front of it and quickly be done with it? So that's the ultimate goal of the project. Hopefully my project will save people from having to manually audit certain things like null pointer problems ever again.
So is there a trade-off to study here, though, where an automated fix may not be as efficient or perhaps even encompassing a structure as you might get in that manual process?
We are focusing on categories where the penalty for fixing a false positive is very tiny. Okay. I mean, if you have a pointer that might be null, then just asking if it's null is a very quick operation on the actual platform. And if the pointer can never be null, then what you've added is a redundant check. Maybe your compiler can tell the check is redundant and just optimize it away. At the very worst, you're going to have just a very tiny slowdown on the program. There are, of course, a lot of vulnerability categories where you can't necessarily do that. A use after free, for instance, could be solved by adding a or moving the call to free later. But if the use after free is a false positive, then moving the free later might make the code much worse. And so that would not be something that we would try to automatically repair, because we'd have to know whether it's true or false before we try to repair it.
I see. So that's where you might have to have more dynamic as opposed to a static analysis to really determine some of those fixes.
Right. Dynamic analysis is that's not something that we have looked into, but that's certainly a potential place for future work.
I see. And how much do you have to understand about the context of a vulnerability in order to do an effective repair?
So in the case of null pointers, you don't have to do much context at all. All you have to know is that this is a pointer, and it might. And in our case, we're relying on external static analysis tools to say, this pointer might be null, and we're not doing our own static analysis. There's plenty of static analysis tools out there that can do that job for us. So we'll just trust that if your tool tells us null pointer on line 10, we'll just assume it's true and repair it, and check later on.
Okay.
Or not all.
Well, this sounds difficult enough, just if you have got the source code and trying to do that. But Will, one of the things you're trying to do is to do some things with binary code. Can you actually talk a little bit about how binary code makes this even more challenging?
Yes, definitely. So, of course, one aspect of it is just like the engineering aspect of trying to decompile the code into something that into a higher level representation, and just that is very difficult. But for my project in particular, there's a few extra challenges that might not be present for other types of decompilation. So in particular, with what we're doing is we're trying to trace sensitive data as it flows through the program. And in order to do that efficiently, we need to use abstractions of the memory. So for example, if you have two arrays, we need to say like, oh, this array can be tainted, but this one can't. But if the array is like 10,000 elements long, we can't like point to individual elements of the array. We need to say this array as a whole is tainted. Now, a problem with working with binaries is if you have these two arrays laid out in memory right next to each other, you don't necessarily know that they are two separate arrays. You might say that, oh, this is one big array. So if you work with the binary, you might say, oh, this whole array is tainted, and then you would have a lot of false positives. And that also comes into play if you use structs in C. If you have an array of structs, that might be decompiled into just like an array of a flat array of integers or a flat array of pointers. And then again, trying to model that precisely becomes a difficult, because we don't because we basically treat every element of the array the same. But if you were going to have like an array of structs and you flatten all of the individual parts of the struct together, well, of course, then you lose a lot of precision. So that, I think, is the main difficulty with this project, is that when you do the decompilation, you do not recover all of the abstractions that were present in the original source code. It becomes just like blobs of data, and you don't know like where one blob ends and where the next blob begins.
So in other words, in the binary, you're farther away from what the programmer originally intended.
Definitely.
Which is somewhat available in the source code, but even more available if you could talk with the programmer. But you're over here in binary land where you just have ones and zeros.
To make it even worse, I imagine the degree of optimization also comes into play here.
Definitely, yes.
Yeah.
Right. So things that might be like easy to analyze in the original code, once you do optimizations, that might make them more difficult to analyze. Yes, definitely.
So Justin, we've been talking about all the stuff that happens when things go wrong.
Right.
But you've got to somehow be able to form a flexible team in an organization that has very specific constituencies that deals with whatever problems they're going to have in this way. So what is the way that you kind of are going to approach this without creating a single blueprint?
Yeah, so that's a great point, because as you point out, different teams are going to do different things, and we see in the example here, depending on what you're doing, you're going to have a different approach. So the knowledge base, what we want to do with the knowledge that we're kind of gathering and the data that we're gathering is to build what's called an ontology. So an ontology is just a way of representing knowledge. But further, an ontology uses something called description logic. And description logic is just, it's a formal representation language. It's not as expressive as like a first order language, but it's still very expressive. And what it will allow someone to do when they're interacting with this ontology is to sort of go through and find the areas of interest that they want to apply to their security operations or their security operations center, and sort of pull out what elements do I need to bring in. So, when we talk about an ontology or talk about description logic, it breaks knowledge down into objects, classes, and then traits or characteristics of that knowledge. So in the case of a SOC, you might have something like, your class is tools or technology. And within that class, you have objects like a SIM solution or a firewall, a next generation firewall, so on and so forth. And they may have different characteristics based on configuration. So if you know your security organization wants to fulfill a certain task, you could go in and say, okay, I want to do vulnerability analysis or code analysis or something. And in that ontology, if you pull that thread, it will bring along with it, okay, that object or that class is connected to all these other objects and classes that you will need to fulfill that function. So it may say, to do vulnerability analysis, you need a static analysis tool, you need a vulnerability management tool, and you need people with certain skills. So it groups that knowledge and makes it easier to sort of pull out without you being the expert yourself.
Okay, so is this the kind of expert system or tool that might not only help to establish a SOC, but evolve it as things change? Because it sounds like, let's say that we get some of these additional capabilities that are coming out of Will or David's research, that could change the nature of the SOC that's actually created, yes?
Yeah, what we're hoping to have when we finish the research is something that can help with an iterative approach. So you're iterating a SOC, whether it's from nothing to like an initial operating capability, or if you already have a capability that you're operating, but you want to add new capacity or add new services that SOC might offer, you can kind of go back through and see, well, what else do I need to add in terms of people or technology or processes?
Does this result in a tool that anybody can use?
The ontology, hopefully the ontology will be something that is available. And there are a lot of other ontologies or knowledge bases connected to cybersecurity out there. So there's some that we might be able to integrate with and include some of the knowledge that we've found and share that with the community.
That sounds great. So David, coming back a little bit, I mean, it sounds a little bit on the surface like these are three completely different kinds of things, but how do you think these three projects are related?
That's what we thought at first too when we first discovered that we were a team. So we got together and sat down, and we came up with two main things that we have in common. The first is automation. We're all about automating processes which right now are painful to do with manually. In my case, I'm automating repairing of lots of little alerts. Will is automating the problem of binary analysis, and Justin is automating the problem of SOCs.
Yeah.
And the second thing that we realize that we have in common is that we all are interested in how ChatGPT might make our lives easier.
Okay.
I suspect that may apply to all the other projects going on here too. I don't know.
So that's it. Will, I'm going to come to you next for this, because a lot of what you're kind of working on, people are now speculating that basically the LLMs that are doing code generation, the LLMs that are doing this are going to be key to trying to get into the identification of some of this malware. Where do you think the evolution of large language models and various capabilities like this fit?
Right, so that's a very good question. So one idea would be to just use an LLM directly, give the LLM the code base, and let the LLM trying to decide if it's malicious or not.
I'm curious whether that would work.
Yes. So there's a few problems with that. One is that LLMs have a fixed-sized, relatively small context window.
Yeah.
So you actually cannot just give the LLM the entire code base. You could give it to it in chunks, but then you need somebody to tie those chunks together, and then it gets pretty complicated trying to do that. So the other thing is that the LLM would basically need to do the same work that our static analysis tools already do to find a lot of this information.
Yeah.
So it would actually be computationally a lot more expensive. These LLMs are not very cheap to run. So I think actually a hybrid approach using some static analysis and then augmenting it with LLMs would probably be the best approach. Like, for example, in my project, we can use static analysis to detect flows of sensitive information, as well as when the program performs sensitive operations. But then there's a question of we have this behavior. Is this behavior malicious or not? Right. And there might be like some like conditions that we think, well, maybe this is a suspicious condition. Maybe it's just like some standard error handling code. So one thing that we could do is after we do static analysis and get some intermediate results that would fit within the LLM's context window, then we could give that to the LLM and say, does this look suspicious or not? And we can give the LLM also a plain English description of what the program is supposed to do. And then it could, now of course there's some question of reliability. Will it actually give you, can you rely on its outputs? But at least maybe if you have like too many results to filter through already, then you could at least use the LLM to prioritize which ones you want to look at.
Yeah, one question I had actually for you before was simply, would an LLM be able to infer not what the code's actually doing, because the code's crashing right now. Yeah. What did the programmer intend for the code? Can the LLM bring you closer to the original programmer's wisdom? Another open question.
That's amazing. And thinking back to the last panel we had as well, is the knowledge that we have on static analysis tools and the history we have of really understanding things like taint analysis, does that have a parallel in terms of the physics-informed networks, a way of helping an LLM in the future perhaps keep from hallucinating and keep from going off into the wrong way?
Oh, yeah, that's a very interesting question. That I think would definitely be interesting to study. I mean, LLMs definitely have lots of problems with hallucinations. I don't know if anyone has solved it. I don't know if it's even possible to solve in general, just because of their stochastic nature. You might, maybe with certain advantages, you can bring the probability of hallucinations down small enough, but it's definitely an open research question.
Well, we have a lot of other research, as you know, going on to really understanding the confidence levels and areas of identifying whether or not a model is confident in its own results. And that's a topic for another day, but it's certainly one that we've spent some time studying as well. Justin, when we come into sort of the tools that you have, I mean, a lot of it is this codification of the ontology and really understanding the ontology portion of that. Do you see a way in which things like the modern generative AI is going to pair with this in order to help even accelerate the adoption of SOCs?
Yeah, so we actually started kind of with ChatGPT. We said, well, can ChatGPT, can we just say, how do you build a SOC? And that would have been a very short research project. We'd be done. But the thing with LLMs is the first L stands for large. You need a lot of information. You need a lot of data to successfully apply that type of AI system or solution. So the more expert field that you drill down into, the less information there is out there about it, so the less effective that is. So when we're getting into something very niche like building a SOC, there's just not enough out there. So when we approached actually an on-campus collaborator here at Carnegie Mellon about this and kind of started talking to him about how can we solve this problem, he said, well, we need to work back from LLMs kind of, and that's how we ended up at expert systems and description logic, which have been around for decades, really. Yeah. In fact, he started by handing me a textbook that was from the 80s, and I said, this is as old as me. But that's where we started, and we had to kind of work back to the expert systems and the description logic, because those kind of do the same thing, but instead of using large language models, we're doing a lot of it ourselves with the analysis and building some of those relationships and doing all that.
That sounds great. And it does really talk about the value of the kinds of expert systems that we had long before LLMs were ever invented, and long before we had transformer models and these kinds of LLMs. So I'm glad that you have that expertise and can sort of bring that into the fore this way. David, I want to come back to change topics a little bit, and I want to get back into some of the details of what you're actually looking at when you sort of get into code and you repair code. Because one of the questions that we might have is, if you're going to get false positives and you're going to repair code that is not in fact broken, what is that going to do to the performance of the code overall, and why repair things that might be false positives?
Right. Good question. So if something is a false positive, that simply means that the tool said, this is a problem, but it's not really a problem, and a human being can look at it and say, this code is perfectly good. And repairing the code, as I said, there are some examples where repairing the code is going to break it, such as if you have a use sector free and you move the location where the program is freeing the code. If the program wasn't bad before, it's bad now.
Yeah.
So we're restricting ourselves to cert rules or CWEs that are automatically repairable. Null pointers are a good example of that. Another one would be integer overflows. You can easily check if an integer is overflowing, or if a potential integer addition might wrap, and indicate an error if that happens. If a false positive is repaired, then what happens is you wind up doing this check. The check always winds up being false. There's no overflow here, so you wasted a few microseconds doing a check, and so it impedes performance slightly. If the code is performance critical, then that might cause more problems down the line. I've actually been looking at some embedded code where they said we don't care about performance.
Right.
That surprises me, but okay, they're not. They have a very different attitude towards performance than I was taught when I first started working in C. So one of the things we are going to test with the repair is not only does the repair work, not only does it produce the same output as the code did before, but how much performance slowdown do you get? The experience that I've heard from people on the C Standards Committee is that if some particular fix or change impedes performance by more than 5%, it's a no-go. People won't stand for it. So you definitely want to have better performance than a 5% slowdown.
Well, the future is coming like a train barreling down the tracks, for those of you that could sort of hear a little bit in the background.
And I just went into a tunnel.
In sort of this. But one of the things is, are we creating really a dichotomy of software that has real-time constraints and has to be very, very carefully constructed versus code that has a lot of, potential flexibility with regard to more fixes are possible, even if the fixes are not strictly required?
I'd say we created that divergence. I'd say we created that in the 90s.
Okay.
Because the 90s was when you had the emergence of language like Java and Python, which were admittedly slower than C. We had C++ too, but that was not slower. So Java and Python were basically picked up by businesses who wanted to spend less effort building programs, and to counter for that, they were willing to sacrifice more computer effort. Mm-hmm. Let the computer do more work, and let the geniuses do less work.
Yeah, which I think is more and more often in a lot of these areas that we're looking at. There is an area of very critical code that's in there, but it does seem to be like it needs a different set of processes, sort of a different way of looking at it than most of the code that we deal with.
There certainly is code that is critical and that it tends to run in embedded systems. As I said, I was surprised at this client that didn't care about performance, but most of them do, and they have to worry about it, especially because they may have race conditions with their threading if they're not careful.
So it's funny you should say race conditions and go into that area, because Will, one of the things I wanted to talk to you about a little bit is often malware and malicious behavior that's inserted into code can't be detected on an individual API call or an individual, even small flow, but on a sequence. So what can you do about sort of the sequence of API calls or sequence of system calls that might be indicative of malware?
Right. So in our project, we do not explicitly look at sequences, but we do implicitly look at them. And the way that we do that is often if you have a sequence of API calls that is indicative of malware, you have information flowing, like you have one API call that provides information, and then you use that information in another API call. So the way that we would handle those sequences that are indicative of malware is to look at the flows between them. Like you might have one flow that opens up a network socket and you get a file descriptor from that function, and then you use that file descriptor in another area of the code where you send sensitive data over the network. So with that, by looking at how information flows between the various API calls, we can kind of reconstruct that sequence that's indicative of them.
Okay, and is that you're already seeing that in the results of the work that you're doing today?
Yes.
Oh, that's really interesting. So that was not something you started with, or that you thought we were going to go off into.
Right. I guess it was kind of emergent that.
Emergent results.
Yes. Yeah.
Well, then that's actually interesting. You get these emergent results in the research that actually come out. Justin, I'm going to turn back to you a little bit there because, in the way of capturing the knowledge for all of the different SOCs that come out, do you see areas emerging in the capture of this knowledge that are either surprising or interesting compared to what a normal consultant might do to go out and do a SOC startup?
Yeah, so we kind of started with the assumption that there are normally three sort of pillars that you build a SOC on: people, processes, and technology.
Yeah.
And as we went through the process of gathering data and gathering information from experts, we interviewed dozens of experts from around the world, different settings, people with experience in government, private sector. And a couple themes emerged. One was that, yes, people, processes, and technology are important, those three pillars. But we sort of found two other pillars that were really essential as well. One was planning, and one was organizational considerations. So the planning was really, what is the process you're going to use to build this SOC or to build this organization? And that had really important effects on the final outcome or the final look of that SOC. And then, of course, the organizational issues. And those were, I think, maybe a little more expected, but there were things like budget, staffing level, and mission and things like that. But that was kind of surprising because we thought everything would fit neatly under people, process, and technology.
Yeah. So how does this actually relate to differences in sort of personalities, backgrounds, KSAs, things that the individual brings to the table? How much does that really perturb the knowledge that you're encoding today?
You mean the differences of the experts?
Of the individuals that are actually going to form the SOC. So
right,
whenever you walk into a potential SOC situation, right, you always have to deal with the people that are there.
Yeah.
The backgrounds they have, the personalities they have, the knowledge, skills, and abilities. How does that interact with the ontology?
Yeah, so a lot of that type of thing is getting kind of coded into the organizational and the planning processes. That's where those things sort of started to emerge, and we were very surprised. It can be very personality driven. Okay, we want this SOC to fulfill a mission. Well, the way someone interprets that mission can be very important, because they may see it as very critical, let's put all our resources here, or they may see it as let's spread things out, or different people may focus on technology or may focus on the people aspect. Whoever's doing your planning may have different biases for or against open source, right? So there's all these different ways that the personality can affect it. So we kind of put all of that into organizational considerations, and we're trying to draw out some of those threads and say, how do you account for having a bias for or against open source tools? How do you account for having a bias towards a people-driven SOC versus a technology-driven SOC? So those are some of the really challenging things that we're working through as we do this coding and build out this ontology.
Yet another reason you can't really have a SOC in a box.
Exactly.
It really does take all of this knowledge interacting together to get an effective SOC put together.
Yep.
Okay, so what I'd like to be able to do now is have each of you think a little bit beyond your current project. So we know that all three of you are going to be wildly successful in coming into it. Once you are wildly successful, what comes next? David, for you, what's next?
So what comes next for me? My dream here is simply that a lot of alerts, of static analysis alerts, no longer have to be looked at, and because they're dealt with automatically, and therefore people can focus just on the alerts that require manual attention. Buffer overflows, for example, use after freeze. So getting rid of the ones that can be automatically repaired means we can actually focus on the ones, because right now there's so many of them that people don't have time to look at them all, and they ignore all the ones except for the most critical ones. So they'll look at buffer overflows, and they may not look at race conditions, for instance.
David, can you imagine this being incorporated into the advances in automated programming that we're having and the advances of Copilot style programming and those elements? Is this something that long-term I would expect to just say, when I write code, it will just fix it on the spot?
Very much so. Think of when you're running a Word document and the spell checker comes over and you said you made a typo over here. Exactly. The same thing should be happening if you're typing in a programmer software like VS Code. It should say, you're not initializing this variable here. You should do that.
That's fantastic. Will, what about you? What comes next after after you've got all of this nailed down?
Right. So after we have the detection piece down, I'd actually like to work with David on the next step, which is automatically removing malicious code. Because, once you've identified the code, it's still there. You need to get rid of it somehow. And you don't actually mess up the rest of the code. You don't want to break the rest of the code base if you're going to remove this piece of malicious code. And trying to do that automatically might be more challenging than just removing vulnerabilities, because you don't know how it might interact with the rest of the code. But maybe using LLM technology, we might be able to at least provide some suggestions to the developers of how to get rid of this malicious code without breaking the rest of it.
That's fascinating. So just speculating a little bit, the world is becoming a much more complicated architectural place. The thinking about code as a monolithic single thing just doesn't work anymore. Even in your original example of the sort of SolarWinds example, wasn't a single monolithic thing that you could just identify and remove. So how does that change the nature of the way you think about this in the future?
Yes, that's interesting. So I guess especially going back to LLMs, if it's spread out across the code base and it can't fit in the context window, then I think LLMs by themselves won't be able to do it. But we probably would be able to do a hybrid approach, like having LLMs plus static analysis, where we can identify the parts of the code base with static analysis, then kind of summarize the rest of the code base, and then identify the various pieces, put them together, give them to the LLM if it fits in the context window, as long with a summary of the rest of the program, and then it might be able to give you something reasonable.
That's great. So if our future SOCs can rely on basically elements of code that will find vulnerabilities and fix the malware that comes in and identify all of that, what is that going to mean for the creation of future SOCs? What does a future SOC look like in a world with all of this new automation?
So I think that maybe plays into somewhere where I'd like my research to go, which is thinking about how you integrate new capabilities and new tools. And when we talk about what we're doing with taking the expert knowledge, building that ontology, what happens when you have a new class of tool or a new capability? Or when things in the industry, in cybersecurity change, how do you integrate that now into the process of building a SOC? And I think that's an open question. So I don't have an immediate answer for you, but it's kind of where we'd like to go next.
Again, it's where the curiosity really gets you to dig into some of these areas to say, what if?
Yeah.
I was going to joke that Will and I were going to make your life harder. But I actually prefer thinking of it that we are actually making your life easier, because in theory, the SOC should be doing these things that we're trying to automate, and they're probably not because they're so painful.
Exactly. Yeah.
So we're making your life easier. You're welcome.
Yeah. So the three of you worked a little bit together before you came on this panel. Did you gain any insights that you want to share with the folks that are watching on what it took as you begin to collaborate together? Did you gain any personal insights into this collaboration?
I think that there's a lot of different specialties, within cybersecurity and software engineering, and I think being able to leverage that knowledge and that expertise really benefits all of the projects. I've learned, from talking to them about their projects and code analysis and things like that, and hopefully you've learned a little bit about SOC operations and things. So having that environment is really helpful.
Yeah, I think the collaboration actually tends to spur the curiosity and the creativity, and I'm very glad to see that happening here in cyber. I know it's happening across our divisions as well. I want to thank all three of you greatly for not only your very detailed technical presentation that's available for any of you to see, but for the interaction here to help everybody understand a little bit better how to place your research in context. So thank you so much for that. I really do encourage all of you, please go to the site to download or to actually stream the detailed technical presentations of each of our PIs in this area. And they will generate curiosity and questions for you. And when they do, please reach out to info@sei.cmu.edu. Really come into understanding what you want to know in addition and how this work might apply to you, how this could really help you become more secure, become more robust, and actually just give you a better capability across everything that you do. So thanks again. Our last panel will begin in a few minutes. We're going to sort of reset here. Please enjoy the promo videos for the last panel that we have. Don't go away. We saved a really good one for last, and thank you for listening.
Hello, I'm Daniel Justice, a software developer at the Software Engineering Institute. In the never-ending advancement of technology, we're leaving the noisy intermediate-scale quantum computing era behind, also known as the NISQ era. From this, we are starting to see the beginnings of practical quantum compute, which promises computational powers unimaginable from their classical counterparts. For the foreseeable future, however, the path forward remains unclear, which leads us to ask questions such as, can we utilize the full potential of this technology? How can we integrate quantum computing into our existing software systems? At the SEI, these yet unanswered questions were the inspiration for our exploratory research into quantum software architecture. Our mission? To lay the foundation needed to bridge the knowledge gap and to ensure that as quantum computing becomes mainstream, our customers are not just ready, but ahead of the curve. We investigated the issues software architects are likely to encounter when integrating quantum components into their systems. Attend my talk at SEI Research Review on November 8th to learn more about our findings.
Hi, my name is John Wolbier. I'm a senior research scientist and the Advanced Computing Lab lead in the AI division at the Software Engineering Institute. I'm the principal investigator for the Co-Design for Edge Artificial Intelligence project. In the resource-limited environment of the tactical edge, it is critical for electronics to be as efficient as possible to optimize mission metrics such as flight time by lowering energy consumption. One method of increasing efficiency is to design an application-specific system-on-chip, or SoC. An application-specific SoC is a chip that contains specialized system components for an application. By creating SoCs that are specific to a particular application, we can eliminate unnecessary hardware and significantly improve the energy efficiency of the overall system. In my presentation, I will discuss how to make an application-specific SoC, particularly how to identify hotspots of an application that can be accelerated, and examples of tools that are available to create an SoC. In addition, I will demonstrate how we implemented this process in our own lab, discuss prospects for the future of this work, and provide open source resources that are available. Please join me at the SEI's research review to hear more.
Hello, I'm Daniel Justice, a software developer at the Software Engineering Institute. In the never-ending advancement of technology, we're leaving the noisy intermediate-scale quantum computing era behind, also known as the NISQ era. From this, we are starting to see the beginnings of practical quantum compute, which promises computational powers unimaginable from their classical counterparts. For the foreseeable future, however, the path forward remains unclear, which leads us to ask questions such as, can we utilize the full potential of this technology? How can we integrate quantum computing into our existing software systems? At the SEI, these yet unanswered questions were the inspiration for our exploratory research into quantum software architecture. Our mission? To lay the foundation needed to bridge the knowledge gap and to ensure that as quantum computing becomes mainstream, our customers are not just ready, but ahead of the curve. We investigated the issues software architects are likely to encounter when integrating quantum components into their systems. Attend my talk at SEI Research Review on November 8th to learn more about our findings.
Hi, my name is John Wolbier. I'm a senior research scientist and the Advanced Computing Lab lead in the AI division at the Software Engineering Institute. I'm the principal investigator for the Co-Design for Edge Artificial Intelligence project. In the resource-limited environment of the tactical edge, it is critical for electronics to be as efficient as possible to optimize mission metrics such as flight time by lowering energy consumption. One method of increasing efficiency is to design an application-specific system-on-chip, or SoC. An application-specific SoC is a chip that contains specialized system components for an application. By creating SoCs that are specific to a particular application, we can eliminate unnecessary hardware and significantly improve the energy efficiency of the overall system. In my presentation, I will discuss how to make an application-specific SoC, particularly how to identify hotspots of an application that can be accelerated, and examples of tools that are available to create an SoC. In addition, I will demonstrate how we implemented this process in our own lab, discuss prospects for the future of this work, and provide open source resources that are available. Please join me at the SEI's Research Review to hear more.
Hi, and welcome back to our final panel for the 2023 Research Review at the Software Engineering Institute. We saved a great panel for the last one. We're really going to be looking sort of more into the future, and as I've done with the other. So, John, please.
Yeah, sure. So I'm John Wolbier. I've been with the SEI for about 5 years. I studied electrical engineering way back when, and I went to Los Alamos National Laboratory, where I focused on computational physics and high energy density physics kinds of problems on HPC systems. I sort of got more interested in the compute aspects of those calculations and away from the physics a little bit. That sort of led me into performance engineering. And from there, I joined up with the SEI, and we've really been talking about new hardware design for AI kinds of applications. And that's what the project is that I want to talk about.
That's really great. Dan.
Yeah, thanks, Tom. I'm Dan Justice. In the past, I was a field engineer before I was at SEI, and specialized in piping, and then I had a career shift, and I came here about 5-ish years ago, and since then I've been specializing in quantum computers, and I act as a software developer and research on that front. Historically, like previously, we've done most of our work at the algorithmic level. We've been the cybersecurity level. But this last year took some time to kind of go up the levels of abstraction and look at the software architectural concerns that happen when you introduce a quantum computer into your existing software stack. So it's kind of an effort to rethink how we're doing quantum, start at the top of the abstraction layers and work our way down closer to the hardware.
So let's stay with you for just a minute.
Yeah.
In your current project that you're in, what are the key research questions and things that you're really kind of struggling with on your current project?
Right. So our key research question is more or less, can current understanding of software architecture and the tool set has accommodate introducing quantum computers into it? There's a little bit of hint that it would struggle with it, simply because if you look at how machine learning has affected that field, it's really stretched its limits. But from our perspective, we think that software architecture already had the tool set to handle it. It just kind of needed to be refined and stretched and massaged a bit. And you can see now that when people talk about machine learning systems, they do so, and many of them are talking quite easily. They have the vernacular for it, and the systems are being architected out from the beginning. They're not just ad hoc anymore or just pure craftsmanship. And quantum systems that are using quantum aren't showing this quite yet. We've actually found over the last year that most people don't have the vernacular or even the ability to talk about things such as what quality attributes do you need to maintain if you introduce a quantum computer, or do you know which quality attributes you're attempting to maximize if you do bring it in? What's your motivation for a quantum computer? Most people hear that quantum computers can speed up their computation and they want to go for that, and they're not so knowledgeable yet on the trade-offs that could potentially happen there. And so that is also one of the challenges that we've had, is simply that there's a gap between not only what quantum computers promise and what they currently can do, but also with how people understand that gap. And that's been one of the largest challenges that we've had.
We've been talking about quantum computers as if they're one thing, but aren't there dozens of quantum architectures that have to interface this way?
Right, and this is where also architecture itself is a word that starts to get overloaded, because there are different architectures for the qubit type. We haven't actually landed on a transistor type yet. So, everyone's trying to get their best qubit out there, and that has architecture. The way in which you connect those qubits is a type of architecture. The way in which you have hardware that controls that, classical hardware to control that, is an architecture. The software control systems for that is an architecture, and it goes all the way up. That was another struggle of ours, was to disambiguate which architecture we are talking about, and we are talking all the way up at the application level and trying to see what that looks like. But we're looking at what I call the Cambrian explosion of quantum technology right now.
Sounds like quite a challenge. John, where's your focus on the current project? What are your research questions that you're struggling with in the project?
Yeah, so I don't know if you've talked about this before, but the SEI has 3 different kinds of projects: a 1-year, a 2-year, and a 3-year. Where as you get to the longer projects, they become more of a transition kind of activity, where we actually want to get the hands in, or the results in the hands of users. And so this project, to make application-specific system on chips, is the 3-year project. And so this is really about sort of technology demonstration for technology that's in often cases quite immature. So we were sort of introduced to this work, and we got into this work by some other work that we do on the behalf of DARPA, Defense Advanced Research Projects Agency, and we saw the technology that was being produced by this one particular program, and we thought, hey, we want to actually be able to try to do that as well. So, and given our sort of unique view into that program, we could say, hey, we like this technology, we like this one better than this one, and let's pick the ones that we want, and then moreover, let's find an application, a DoD application, to apply this technology to try to create this domain-specific system on chip. And so that's what we're doing. We found an application. I won't talk about it here, but we have a code base, and we're trying to design domain-specific system on chip for that code base. And so the biggest challenges really are about the maturity of the technology that enables that. And ultimately we're trying to come up with like a almost like a formula. So if somebody had their own application and they wanted to do this kind of activity, we would point them to you do this, then you do this, then you do this. That's just given the complexity of the whole thing, that's a stretch. Yeah. But so we're in the phase sort of each of those do thises is really complicated by itself. And so we're sort of, and it's emergent technology, and so we're sort of working through all those different phases of the process.
Now you're working in parallel with your FPGA work and the accelerators that you're essentially architecting, overusing the word again, on the chip. With places like the chip fabs that are doing very large and longer term manufacturing of these kinds of accelerator chips. How do you interface with the world that's trying to build these chips at scale?
So at present, our project is really focused on targeting field programmable gate arrays. Mm-hmm. So these are chips you can buy from your local convenience store and program them because they promise such higher energy efficiency, et cetera. The project also does lead towards a path where one could do their own design, that as in design the application-specific integrated circuit, a specific piece of silicon. And one of our collaborators on campus is Dr. Ken Mai, and he's got experience in that. But that's all in the context of this project. It's a little bit of a stretch goal to actually do the SoC design and certainly the tape out. But it's a really sort of exciting time in the semiconductor industry right now. You read about all the CHIPS Act is investing hugely in domestication of semiconductors. Yes. And so it's quite a great time to be around in this field.
That's really exciting. So, as part of the way that you're looking at the research and coming into it on this project, what kind of performance gains can you actually expect on the system on a chip? Do you have any examples?
Yeah. So I mean, not specific examples yet because we're sort of too early in the technology stack, at least regarding our specific application we've chosen. But given my HPC background, I can tell you that if a code and I'm thinking now of more like a physics kind of code, if it can achieve 1%, it's probably average, 1% efficiency, right? So if you have, I work with some folks who did CFD, and there's this one guy in particular who is well known in the field. He could get 10% efficiency, but that's unheard of almost. And his code was always so very specific that it wasn't sort of a general need that Department of Energy had at the time. Right. So when you start to think about efficiencies, start to think in the tens range or 10 or less. With these techniques, the estimations are that we can get up to 70-80% efficiencies, and it's largely because a CPU has a lot of stuff that a specific application probably doesn't need and isn't going to use, but it has to be powered on while the thing's running. So it's largely about eliminating unnecessary pieces and then designing specific pieces for the applications that you have. For example, like a fast Fourier transform.
So that sounds like in a deployed environment, you could get significantly either more time in the sky or elements around. I mean, power is capability in the field, right?
Absolutely.
Yeah, that's really incredible. But sort of talking about those kind of gains, let's go back to quantum for a minute. Quantum has tremendous promise this way, right? But I'd say to date, we haven't seen too much in the way of quantum supremacy.
There has been two experiments that have shown that. One was made by Google about, I want to say 2 years ago, and maybe it was 3. And then approximately 12 months later, there was one made by China, and it was a pretty similar replication of the experiment that Google produced. And what they did was they were able to create a quantum random number generator that outperformed any classical random number generator. So that does exist. The usefulness of that is still up for talk. But no, more complex and more perhaps tangible use cases are still wanted. Yeah. However, I will say quantum computers are still very much in their infancy. We are talking very few quantum computers break even 100 qubits. Yeah. The largest one's around 400 qubits right now, although I personally haven't seen it myself. And while this is a surprising amount of compute power, there aren't too many applications that we've ever really successfully done with 400 bits. So we still have quite a few doubling periods to get somewhere useful. And if so I would just wait a couple more doubling periods, right? And we have been doubling recently, pretty consistently.
Right. So, I mean, one metric we have obviously is the number of qubits and the doubling frequency of just the number of qubits that are available. Are there other key areas that are keeping us from realizing the performance gains that we might get in a quantum hybrid architecture?
Yeah. So the one of the biggest ways is just interfacing with it.
Yeah.
Data input and output is proving to be a really large challenge. Especially with the fact that you have what's called the no cloning principle in quantum computers, where you cannot copy data from one qubit to another, and this also means you can't copy information from a quantum register into another. And so this leads to a lot of games that have to be played even at the highest levels, and a lot of awareness by your architects and your algorithm designers. And it's been a real bottleneck of how to either circumnavigate that or work with that. It's not so much fun when your data disappears every time you try to use it.
That's a little bit of a challenge. So within the project that you're working on and the architectures you're trying to put together for these hybrid systems, do you have approaches that are gonna help this issue?
Wow. Help is perhaps a strong word at this case. I would say we've more or less identified problem areas, this being one of them, scalability being another, education and workforce development being quite another. But no, there are no real solutions yet. They're just trials.
Yeah. So when you characterize the way that you're sort of characterizing the problems that you're identifying on here, can you identify them in specific enough ways that the research community can sort of build upon this?
Right, yeah. So it would be, first off, identifying what type of quality attributes that you're interested in, right? There are certain quality attributes that we've recognized people just aren't too interested in. So.
Right.
Which is not always where you see a lot of effort being put. So surprisingly, at the moment, interoperability seems to not be a hot button topic, even though you see a lot of people and even companies focusing on that problem. Right. Most people right now are interested in just getting it to work, to see that quantum supremacy that you're talking about. And so you're going to be looking at things such as efficiency. You're going to be looking at things at scalability, and performance capabilities there. You also want to look at and make sure that these interfaces are actually operating, because right now our classical systems are so inefficient with how we interact with quantum computers that it's actually taking over the majority of the compute power.
Yeah.
There's papers out there claiming that if you want an error-corrected qubit, each qubit is offering up close to a gigabyte per second of data you have to munch through, and that just can't exist. Like that's not practical. That's not scalable.
Right.
Those kinds of quality attributes are where we need to focus on in order to make quantum computers practical.
So this really does get into the early, you said infant nature of where we are in quantum computers.
Yeah.
So how does the collaboration with the academic world really help with this?
Yeah, so it does two things, right? So we're starting to build up quite the collaboration here in Pittsburgh through the Pittsburgh Quantum Institute, which is a connection between Duquesne, University of Pittsburgh, CMU, and also with Pittsburgh Supercomputer, which are really ramping up their resources with our help in order to do quantum research. And this allows students to come in, and this is beautiful because one of the things that students give you is a fresh insight, a huge amount of optimism, and an amazing capability to just deep dive into areas you may not think would necessarily turn something up, but eventually do. And so the academic side that we have here at Pittsburgh is simultaneously deep diving and also giving us a breadth first search algorithm. And so we now have people doing research, students, faculty, and professionals, all the way from the very top, like what I'm talking about, all the way down to actually building qubits. And a lot of that work right now, I think, is in the algorithms, which I like. But yeah, so we're seeing a huge amount there.
That's really great. Are you still looking for more collaborators and more people to get involved in this?
Always. This is a team effort. This is a huge problem. You can't solve these kinds of problems on your own. Yeah. And so this is going to be a challenge for the next couple of decades at the minimum. And although it's just ramping up, I think.
Yeah. John, so with your system on a chip and the work that you're specifically doing here, again, you're kind of just scratching the surface a little bit too on an area that's quite open-ended. How are you collaborating with the more traditional academics and other people in order to really accelerate what you're able to do?
Yeah, so there's actually kind of a unique collaboration, and it goes back to the thing I mentioned earlier, where we were introduced to this work through DARPA.
Yeah.
So, SEI performs a role as a sort of test and evaluation government trusted partner sort of in that program, and so they get to see all the different performers on the program. You get introduced to their technology, but it sort of the surprise there was that it turns out that they're very interested in us coming and looking at their stuff and providing feedback, and they become collaborators. So that's a sort of unexpected collaboration that has really matured. And like I said earlier, we sort of picked a few of our favorite things that we saw in the program, and we are now, I would say, collaborators with the people that were generating that part of the technology. In terms of the CMU campus collaborator, we actually have Ken Mai, like I mentioned earlier, but then another long-standing collaboration we've had is with Franz Franchetti.
Yes.
So it turns out that the application that we're interested in has to do with, or has a software-defined radio, and so it has typical sort of digital signal processing stuff, and one of the core functions of DSP is fast Fourier transform. Franz has a long history in optimizing Fourier transform. So we've got sort of several of us working together to enable this technology for the applications that we're interested in. Now, it could be that the next person comes along and their application doesn't have anything to do with fast Fourier transform or any signal processing kind of thing. So then you might have a different, you get your subject matter expertise for the particular things that you're trying to go after. And like I mentioned in my talk, technical expertise. So there is all these tools and things to help you do stuff, but deep technical expertise is there's basically nothing that can substitute for that.
Yeah. I can see how that's going to be extremely valuable, not now, but even sort of moving forward, as this kind of continues. So in both of your projects, one of the things you sort of talk about, especially in your in the online talks that I hope everybody is going to go out and look at, is the intermediate representation as a level of abstraction that really helps you to construct the solutions that you need. Can you talk a little bit about how you arrived at the intermediate abstractions that you're using, the representations, and how that really helps to address some of the problems that you're seeing?
Sure. We're focused on a very specific form of intermediate representation because it's a popular activity in the community. And that is something called multi-level intermediate representation, MLIR.
Yep.
It was started by some folks. One of those folks included Chris Latner, who also is the original author of LVM. It was started about 5 years ago ish, and it's a compiler technology. It sprung out of the LLVM idea where you can do optimization passes and something called lowering passes. So you start with a source code, you put this into a a high-level intermediate representation. So your primary object is a tensor, and so you have code like starting to look like assembly code a little bit, but it's operating on tensors, and the optimizations that you do are sort of at that level. Then you lower it. You lower that representation to something that now works, instead of on tensors, it works on buffers.
Yes.
So you're starting to move closer and closer to hardware, and then you can do optimizations at the buffer level. Then you lower it again to like the register level, where these, and each one of these is called a dialect, and the process of lowering is what MLIR enables. Now, so what one would really like in our case, the sort of the holy grail, is I start with my Python, PyTorch machine learning neural network, and I push a button, and what it spits out is a hardware implementation specifically for your function. One of the primary methods that you find in the community are people trying to use MLIR to get from point A to point B. It's early days in this effort, but we're in there, and we're also collaborating with Pacific Northwest National Laboratory. They have a program called SodaOpt that does this. We've picked it up. And we're working with them to try to put it through its paces and get something useful out of it.
Yeah. So Dan, I expect yours is very different than this, but still with the intermediate representation. What's it look like?
So IR became quite obvious of an interesting point to us, actually, because again, we talked about architecture being an overloaded word, and when we were reaching out and attempting to find more collaborators, a lot of others thought that we were actually looking at the IR level. Of course, we're slightly higher than this, but it piqued our interest, and we spent a little bit of time looking into it, and we found that there's quite an effort to have quantum IR, as has to do with quantum. And we found that historically, there is this compiling issue within quantum, because you have to start at this high level circuit description level. We don't have much higher than that at the moment. Actually, most of our programming is circuit descriptive level, but you had to compile down to some sort of control systems. And not only is that stack oftentimes not well defined or slightly hidden, it can change drastically within a single company's stack, or even especially among several company stacks. And so while the ability to target multiple different quantum computers efficiently is not a pain point for most people who are stuck to a stack, there are quite a few out there that are slightly homeless when it comes to which stack they prefer, and this interoperability is very important to them. And leading this effort is Oak Ridge National Lab. We actually had them come and give a presentation at our workshop on software architectural concerns at IEEE Quantum Week this last year. And they're doing something really interesting. They're doing exactly what you talked about, which is they're building out their own dialect. And this is allowing them to target multiple, because they are slightly homeless when it comes, they target multiple different types of hardware, and they're building this out for the entire community. And this is making accessibility to efficient quantum computations much better. So that
sounds really great. So we only have a few minutes left, but both of you are in one of the areas within the SEI that really does focus farther in the future and really look at about future computational models, future of where we're going to go with regard to when we cross that barrier and quantum computing becomes dominant in a number of areas. So beyond your current research, where do you see your work taking you?
So for our project, I have a stretch goal to actually tape out some silicon. So it turns out, I mentioned a little bit the CHIPS Act, investment in hardware, but there's also a very popular open source hardware activity going on with the RISC-V CPUs is an open ISA. The tooling, it used to be that you have to work for a mammoth company to have access to tooling that would allow you to actually do a design. So there are open source versions of all that kind of stuff now. It's all, again, going to be very nascent and sharp and pointy, but I like to see us actually go that route and eventually try to tape some stuff out.
Is this a key area within the lab that you actually have at the SEI? So
I think it's more of a target. Like actually doing a tape out is quite a endeavor. So I would say like our lab, we have some FPGAs in there, we have some Orange GPUs, we have a couple different servers with some modern hardware, et cetera. Everything we're doing sort of is pushing in the direction of eventually trying to do some sort of tape out.
That's great. Dan, what about you?
Yeah, so I think community and community building is going to be the biggest thing, the furthest out. I think the idea is that eventually SEI will help Pittsburgh be a community that people come to in order to have full stack solutions to problems that people hope to accelerate with quantum. Right, and so we hope to have an environment where that's conducive. We do a lot of workforce development here, as you know. We teach classes here. We do research, and we go out and we help people. But short term, I think that maybe what we're going to look more at is, since we started really high and we have to go down. We can't go much higher in the stack. What was the positioning? And so we're going to start moving down. And I think the two fronts that are going to be really interesting in the next couple of years is going to be cybersecurity on the quantum side, especially classical defense to the quantum threat. And then I also think there's quite a lot of interest in quantum machine learning. I think that there's a lot of movement that needs to be done there in order to make it, to push ahead and make it useful in more near-term timeline.
That's going to be excellent. Well, we're just about out of time, so I want to thank you both very much for your insights and for the presentations that you delivered online. They're really good, very detailed, and help understand the research and the context that you're doing. So certainly, please do go to the videos that we have related to the 2023 research review on the website. Take a look at these. If you see or get curious or have any questions or insight into what you want to do on either of these projects, please send a message to info@sei.cmu.edu and really explore. Get into this. This is early stage work, and it's both going to have huge impact as we move forward into the future of computing and kind of in there. So thank you both very much. So with that, that is the conclusion of the live stream portion of our 2023 research review at the Software Engineering Institute here at Carnegie Mellon University. I hope that these 4 panels gave you some indication of where our researchers are going and how we're working together and how we're all really cultivating that curiosity here at the SEI to dig into the ideas and the insights that we get through internal collaboration and collaboration with you and everybody else that has the difficult problems that we're all trying to solve as we move into the future. We do have a number of ways for you to stay engaged with us. They're all going to be available from this live stream. You'll be able to see the links. We have blogs that are very active, very detailed and technical, so you can dig into as much detail as you wish on any of these projects. Access to all of our researchers is open, and we can talk about the research that we're doing here. Bringing your problems to us, understanding what kinds of issues you have, help us to really prioritize what research we need to do into the future. We spend every year a significant amount of time understanding how the problems are evolving, where the existing solutions lie, and how it is that we can interface with the community to make a real difference, both at DoD, the US government, and the world coming into this. So thank you very much for staying with us on this live stream. I hope you enjoyed it. Comments are always welcome and feedback is welcome. Please let us know what you think. And we hope to see you at the future 2024 research review to be announced. And in the meantime, please stay secure, stay active in software engineering, and let's engineer those AI systems of the future. Thanks very much.